expected to turn on your video when you talk. And all the talk in this session is 15 minutes, including 3 minutes questions.
The following message is best viewed on an oscilloscope.
Hello, so welcome to Neutrino Physics Session 4. Let's start today's session. So in this session, mainly we discuss the future project of neutrino physics. First speaker is Dr. Cecile Jollet. She will give us JUNO physics. Please start.
Okay. So good morning. Can you hear me?
Yes.
Okay, so I will share my screen. Okay, can you see it?
Yes.
Okay, so I will present today the JUNO physics program. So first I will do an introduction about the neutrino oscillations with reactor neutrinos. So the reactor oscillation experiments aim at the measurement of oscillation parameters, the mixing angle θ13, θ12, and the mass splittings for the observation of the anti-Newey transition. So the oscillation regime is different according to the distance between the detector and the reactor. This is what you can see on this plot. So at a distance of about 1 kilometer, we will be sensitive to the fast oscillation driven by the mass splitting delta m square 3.1, and that was the goal of the experiment Diabe, Ueno, and Double Show. Which measured the θ13 mixing angle, while at a higher baseline, we will be sensitive to the slow oscillation induced by the delta m square 2.1. So JUNO will be installed at the minimum induced by delta m square 2.1, but it will be sensitive also to the fast oscillation, so it will measure both delta m square 2.1 and delta m square 3.1. So the neutrino reactor experiments are sensitive only to the anti-Newey disappearance. Therefore, they are insensitive to the delta CP phase, and this allows for a clean measurement of the parameters. So the antineutrinos are observed via inverse beta decay process that I will call IBD, which allows for twofold coincidence and so a clean signal. So you can see here the process. The anti-Newey will interact with the proton, and we will have the ionization and annihilation of the positron, which will give you the prompt signal and which will permit you to measure the neutrino energy. And the delayed signal will be given by the neutron capture on hydrogen, emitting a 2.2 MeV gamma. So the energy spectrum is a convolution of the antineutrino flux from the reactor and IBD cross-section, which has a threshold at 1.8 MeV. And so the measured spectrum, you can see it in red. So here it is without any oscillation. So JUNO stands for Jiangmen Underground Neutrino Observatory. It will be located in the south of China at 53 kilometers from two nuclear power plants, Yangjian and Taishan, which deliver 26.6 gigawatt. JUNO will be installed in a dedicated underground laboratory, which will have 700 meters overburden. So here you can find a design of the detector. So the experiments consist of a very large target made of 20 kiloton liquid scintillator detector. It will be the largest liquid scintillator detector ever built. So this liquid scintillator will be contained in an acrylic sphere, and the scintillation light will be detected by 18,000 20 inches PM tubes and 25,000 3 inches PM tubes. So we have a large coverage since we want to detect 1,200 photoelectrons at 1 MeV in order to ensure a very good energy resolution, since the goal of the experiments is to have 3% energy resolution at 1 MeV. Around the central detector, we will have a water churn curve detector, which will contain ultra-pure water, and the light will be seen by PM tubes. Its goal is to have a high muon detection efficiency and also to protect the central detector against the external radioactivity. On the top, we will install a top tracker. Its goal is to perform a precise muon tracker thanks to 3 layers of plastic scintillator, and it is quite important in order to veto the cosmic isotopes, which are source of background. And we will have also what you can see here, the calibration house, in order to deploy multidimension calibration systems to ensure the good energy resolution. So today I will not give details on the detector characteristics, since it is done in another talk done by my colleague in other session. And you can find also several posters on the detector characteristics. So here you can see the members of the collaboration. So JUNO is an international collaboration made of 669 members from 77 institutes spread over 18 countries. So today I will present the physics possibilities of JUNO. JUNO is a multi-purpose neutrino observatory, and it has a rich program in neutrino physics and astrophysics. So JUNO, of course, will detect the antineutrinos coming from the reactor. The goal is to determine the neutrino mass ordering or neutrino mass hierarchy, and to do precision measurement of some oscillation parameters. However, JUNO will be able also to look at the supernova neutrinos, to put constraint on diffuse supernova neutrino background, as well as looking at transient events. And it will be able to observe the neutrinos coming from the sun, coming from the atmosphere, neutrinos, as well as study the nucleon decay. So I will present you these different subjects. So I begin now by the mass hierarchy determination. So the oscillation probability can be written in this following way, where you can see that we can have a sign plus or minus. If the sign is plus, that means that the hierarchy is normal. So the delta m square 3,1 will be positive, and the neutrino with mass m1 will be the lightest one. If the sign is minus, we will have the inverted hierarchy, and so the opposite. You can see here the neutrino spectrum. So in black, it is without oscillation, and in blue and red, this is the oscillated spectrum at the baseline for JUNO. And you can see that we have two cases: in blue when the hierarchy is normal, and in red when the hierarchy is inverted. And so the goal of JUNO is to discriminate between these two hierarchies during a spectral analysis. So to achieve such a goal, several conditions on the baseline and on the energy resolution are necessary. So this is what you can see in this plot. So this is a delta K square between the two hierarchies as a function of the baseline. This is for an ideal distribution, energy resolution 3%, and after having collected 100,000 IBDs. And you can see that we can go up to delta K square up to 16. Then starting from 16 and taking into account of the true core distances, the shape uncertainties, and the background, JUNO will be able to perform a measurement with a delta K square of about 9. But if we take into account for constraints from long baseline, we can do an absolute measurement with a delta K square greater than 16. So the baseline is really important. The other important point is the energy resolution. which is critical, and the goal is to achieve 3% per square root of the energy. So you can see here the newly oscillated spectrum. This is the ideal case at the correct baseline. You can see the difference between the two hierarchies in blue and red. And here in the middle, this is the spectrum when we take into account of the energy resolution. And you can see that the peaks, oscillation peaks, are a little bit smeared. Then looking at the delta K square as a function of the resolution, energy resolution, you can see that it is really important to achieve this 3% energy resolution. So to reach the required energy resolution, several developments have been made. We will have highlighted a large PMT coverage and a good calibration. And to keep the energy scale uncertainty at the 3% precision, a comprehensive calibration strategy is foreseen. Moreover, it is important also to know the reference spectrum with high energy resolution. That's why the collaboration has decided to construct an additional detector, which will be the Tau detector for Taishan Antineutrino Observatory. Its goal will be to precisely measure the reactor antineutrino spectrum in order to provide a model-independent reference spectrum for JUNO, but it will be also benchmarked for investigation of the nuclear database. So the detector design can be found on arXiv. It will be at 30 meters from one of the Taishan reactor cores. It will be a ton-level liquid scintillator with a high coverage in order to collect 4,500 photoelectrons per MeV. You can see here the design of the detector. Its installation and commissioning are foreseen in 2022. So I come now to the second very important subject of JUNO, which are the precision measurements. So by detecting the reactor antineutrinos, JUNO will be sensitive to the solar parameters as well. And so JUNO will perform an unprecedented measurement precision of the parameters sin square theta 1, 2 at delta m square 2, 1, and we will have a measurement better than 1%. So now I come to the solar neutrinos. So for JUNO, it is a challenging measurement since the overburden is quite low, but we are developing new veto strategies in order to reduce the cosmogenic isotopes background. Moreover, the solar neutrinos are not detected via inverse beta decay, but via neutrino elastic scattering. So we need higher requirements in terms of radio purity. So recently, we have a new collaboration paper about this subject that you can find on arXiv. And this paper, we assume an intrinsic radioactivity level of 10 to the minus 17 gram per gram. In that case, we can lower the threshold to 2 MeV. And we will also have a fiducial volume energy dependent cut. So our sensitivity is that with 10 years of data taking, about 60,000 signal and 30,000 background events are expected. And this will also permit to shed new light on the current tension that we have on delta m square 2, 1 between solar and reactor neutrinos measurement, but with the same detector. So for the supernova neutrino, the integrated neutrino flux from all past core collapse events is the diffuse supernova neutrino background. With JUNO, we can observe it looking at the IBD, but after 10, 11 MeV in order to be above the reactor neutrino spectrum. The background is the one coming from the atmospheric neutrinos, but the expected detection is about 3 sigma after 10 years. And in case of no positive detection, we can improve the current limit. For the core collapse supernova neutrino, the golden channel for us is IBD. We expect 5,000 events for supernova at 10 kilo/sec, but we can also have information about the other flowers thanks to the neutrino proton elastic scattering channel. And JUNO is part of the supernova early warning system. So recently, the collaboration has decided to add an additional trigger, the multi-messenger trigger, which has the goal to do a real-time monitoring of the MeV transient neutrino sky. And for that, we want to lower the energy threshold down to about 10 keV. So for the atmospheric neutrinos, they are, of course, a source of background when we look at supernova or proton decay. But using them, we can do additional measurement of mass hierarchy with matter effects. You can see here the sensitivity as a function of the lifetime. When we look at the point-like events, which are the electron neutrinos, or track-like events, which are the mu-mu interaction, we can also look at theta to 3, and we can do combined studies of oscillation from different sources. For geoneutrinos, of course, we have a large background coming from the reactor antineutrinos. But however, thanks to its really large size, JUNO will be able to observe the geoneutrinos with high statistics. Indeed, we expect about 400 to 500 neutrinos per year. And we aim to put a precision of the geoneutrino flux of about 6% after 10 years of data taking. So another important topic of the JUNO program is the study of the proton decay. We will look at this particular channel, which is a decay into K1 plus anti-nu. This permits to have a clear identification, since we will have 3 signals in coincidence, the K1, the muon, and then the Michel electron. And after 10 years of data taking, JUNO will be sensitive to about 10 to the 34 years. So is it the timeline of the experiment? I will not give detail about that. We are an international collaboration since 2014. And so now we are here, and we expect to take data in 2022. So I come to my conclusions. So as you have seen, JUNO is a multipurpose neutrino observatory with a rich program in neutrino physics and astrophysics. The main objective is the determination of neutrino mass ordering and the sub-percent measurement on theta 1,2 and delta m square 1,2. But we can also look at the detection of solar neutrino, atmospheric neutrinos, observation of supernova neutrinos, and be sensitive to the proton decay. The production program and the progress are well underway, and the JUNO experiment is expected to start data taking in 2022. And that's all. Thank you.
Thank you very much. So we have only time for only one question. Do you have any questions? Okay.
Hey, hi. Hi, this is Beda. Hi, Cecile. It's very nice talk. Thank you for that. I have a question about this. When you talk about this, the solar neutrino sensitivity, where we assume the radio purity of 10 to the minus 17. Can you comment on that? How achievable is that? Because it, from my point of view, it's very challenging. I mean, we are exploring Bragg-Sino levels, and they put a lot of effort in that. So can you comment on how JUNO plan to achieve 10 to the minus 17?
Yes, so as you have said, it's really challenging, and only the detector will be able to measure such radio purity. So indeed, in the collaboration, as you know, we are working on this purification using alumina filtration, distillation, gas stripping in order to reduce the radioactivity. We will have also an online monitoring. And in order to control, we should be able to control level purification before to fill the detector at a level of 10 to the minus 16. So all the effort is made in order to really reduce this radioactivity level. So if it is not possible to achieve such radioactivity purity, we know, however, that we can reach the 10 minus 15. And in that case, for the solar neutrinos, of course, it becomes less, we will not be able to reduce the threshold at 2 MeV, but in that case, we will have a threshold at the level of 5 MeV, and so we will also reduce our sensitivity on this measurement on delta m square and precision measurement on the solar neutrinos.
Yeah, okay, thank you very much. Thanks for the answer.
Thank you. Then let's move on to the next talk. Next talk will be given by Piotr Kalaczynski. He will talk about KM3-net ORCA detector and physics.
Okay, thank you. Let me go to full screen. All right, thanks for the introduction. So I'll start off with a brief introduction to KM3-net itself. We are basically a European collaboration mostly, but it's, as you can see, not only. The name itself stands for the Cubic Kilometer Neutrino Telescope, and we have two of those, ARCA near Italy and ORCA near France. The principle of how our detectors work is the following. Here you see an example of an upgoing muon neutrino. So it creates a muon which will travel faster than the light in the water, creating chunk of light which we can then observe. What we do to observe this light are photomultiplier tubes. You see one of our PMTs on the table here, and there is a dissected digital optical module, which consists of 31 such PMTs. On the back, you see a full one, plus there's, of course, some other electronics and other hardware, as you can see. What we do next, we assemble detection units, which are basically strings with 18 DOMs each, and we put them into such, such launchers like here. They have anchors in the bottom and some buoy, so that when you put this all into the water, it will sink to the bottom of the sea. Then you release the mechanism and it unfurls to the top, and then you have a completely deployed DU. By the way, when I will say something like ORCA 4, I mean ORCA with 4 DUs installed. All right. So on the left, you see the dimensions of the ORCA detector, roughly. So we are 2.5 kilometers underwater. And there's, well, everything sketched how it works with an example of a muon bundle event. And also there are cables that go to the shore where we further process our data. So ORCA deals with oscillations. The main goal is, of course, determining the neutrino mass hierarchy. But there is the second detector, ARCA, which I mentioned, which deals with astroparticle physics, and with it, we want to see astrophysical neutrinos. But I will not be talking about ARCA in this talk anymore. As you see, ORCA is also quite denser than ARCA. All right. There are two event topologies that we expect to see in our detectors. Well, already see. Tracks, which come from CC events with muons, and showers, which come from pretty much everything else. Tracks are basically elongated lines through the detector, and showers are just more localized. By the way, here the bold sizes encode the number of hit PMTs on a DOM, and the color shows you the timing information. All right, let's move to the detector status. ORCA is located roughly 40 kilometers offshore from Toulon. The energies that we want to target are between few and 100 GeV, and we run with 6 DUs since January this year. We plan to deploy 3 new DUs before the end of the year, and the full configuration with 115 DUs should be ready in 2024. We already do have first neutrino candidates, as you see on the bottom. This is a neutrino candidate example with 6 lines. In red, you have triggered hits, in blue hits, and the yellow is the expectation. So you can see very nicely how this aligns. We have been operating throughout the COVID phase, actually without interruption, as we routinely operate our detector from afar anyway. And there has been actually a celebration of operating with 6 DUs for 6 months. I encourage you to go through those 2 links. I actually took part in playing in Route 66 myself. It's a little music video. It's really cool. Okay, going back to the business, let's go to the measurements we've done with ORCA. The first one is actually my own work. It's an atmospheric muon rate measurement. On the left, you see the reconstructed zenith angle. And we compare the data in black with 2 Monte Carlos, MuPage, and Corsica. As you see, the downgoing part agrees with the data very well. We do not really expect a perfect agreement for the upgoing part for several reasons. The reconstruction tends to flip the direction from down to upgoing. plus the Monte Carlos are purely muonic, so there is no pure background, pure noise simulation there, and there are also no neutrinos in those Monte Carlos. For the energy on the right, you see that we well agree with the data pretty well over the whole range. On the bottom, I'll stick to this convention for the rest of my slides, that I give you the poster number if it was a poster from Neutrino 2020, as in this case, and also a poster miniature on the bottom right, and also some extra information like the lifetime of the Monte Carlo. In this case, this is lifetime for the data and mu page, and it was collected with 4 DUs, and the rate of the muons I've observed was roughly 400,000 muons per day. Once we have muons, we can of course look for neutrinos, and this is what has been done. On the left, you again see a zenith spectrum in dotted lines before any cuts, and on the bottom in red, sorry, that's my dog. On the bottom in red and black, you see the neutrino Monte Carlo and the data. They agree very well. The purity of the selection is 99%, and we observe a neutrino rate of about 3 neutrinos per day. Once we have this, we can zoom into that part and have a little look at what we can say about the oscillations now. In orange, you see the scenario without the oscillations, and red shows you the option with oscillations. The black are our data points. So you see, we already now favor the oscillation scenario. The p-value is given here. All right, let's go to some sensitivity studies we've done. Of course, we'll start with a flagship analysis, which is neutrino mass ordering. First, a little introduction on the event classes that we use. I've already mentioned tracks and showers, but there is actually an extra class used here, which is a middle class, something in between, basically. Here you already see that the tracks really are new mu-CC events, and showers are mostly new e-CC events. The cuts that we use are the containment cuts, so that we are within the detector. We only select upgoing neutrinos, and we also have some quality selection. Then for the background suppression, we use random decision forests. What we then obtain are 2D distributions of the reconstructed energy and zenith angles. And this, what you see, is assuming the normal ordering for 3 years of data taking with full ORCA. And you can use these three distributions to then assess the sensitivity, which is on the right, by comparing the case for the normal against the one for the inverted hierarchy. And this is shown for all 3 event classes, so tracks, middles, and showers. This is done by minimizing a test statistic and done on a 40 by 40 grid. This is not the final result. The final result is, of course, the sensitivity versus the, on the left, versus the data taking time as a function of normal and inverted hierarchy. We also compare the option without and with systematics. On the right, you see a similar plot, but scanning over theta to 3 angles for both hierarchies and also for 2 different delta CP angles. We basically, from this, can say that we should be able to, if normal ordering is indeed true, we should have 5 sigma discovery after 4 years with ORCA. But this can be done better. We actually had a JUNO talk right before me, and there's a combined analysis with ORCA and JUNO. Then we can employ the fact that there is some tensions between the best fit values for the term squared 3-1 for us, and when you assume a wrong ordering, then this enhances the sensitivity, and you see the same set of plots. So sensitivity versus time and sensitivity versus theta to 3 angle. And in violet, you see the combination of JUNO plus ORCA. And basically, the result is after 1 year, we should get 5 sigma if we work together with JUNO. So it's always worth to cooperate. We of course also measure mixing parameters. So here you see on the left the allowed contours for the normal and inverted ordering with 3 years of full ORCA. And on the right, we also compare with some other experiments. This is assuming normal ordering, and we take the latest published contours from the other experiments. The references are in the backup. Also, the inverted ordering plot is in the backup. All right. We also do a tau appearance analysis. On the left, you see the tau normalization versus the lifetime of our detector. From this, you can see that within a few months, we should be able to confirm the tau appearance with full ORCA. The fit works very robust against θ2-3 and mass ordering. This analysis is also using quite new methods. We use deep learning approach with convolutional neural networks and compare this against our standard maximum likelihood approach, and we see an improvement of at least 10% everywhere. Okay. We also have a bit more exotic scenarios like stereo neutrinos. We use for the analysis the simplest scenario, which is 3+1. So we add one stereo neutrino to the standard case. So we have our PMNS matrix plus some extra elements, which implies, of course, extra mixing angles, extra masses, and extra CP violating phases. And I present here only two main plots from the analysis. You can look into the poster or into the backup for more. Those are exclusion limits, so everything to the right is excluded, so the more to the left, the better. As you see, we are quite comparable to Diabay in this space, and we can even be more sensitive than some experiments in here in this space. Again, we use the latest published results from the other experiments. There is no projections here. This is done assuming 3+1 scenario, normal ordering, and non-zero delta m squared for 1 and new fit values for these parameters. I could not cover everything. There is way more in the backup. So if you want to have a look at non-standard interactions with ORCA or core collapse supernova, dark matter from the sun, or some potential detector upgrades like super ORCA and sending a neutrino beam to ORCA, which is P2O, please definitely do have a look. So that would be all from me. Well, to sum up, the ORCA 6 is running stably. We expect to deploy even more DUs this year. We have first measurements with ORCA 4, and we already do see the oscillations. We work right now on analyzing the ORCA 6 data, and my take-home message for you is, well, ORCA lives and bites hard. There's exciting physics ahead of us. And, well, that's it. Thank you for your attention. I'm happy to answer any questions you may have.
Thank you very much. So, time for questions. Do you have any questions? Yes, please. Frederick?
Yeah, hi. This is again Ben. Yeah, thanks for a very interesting talk, full of like the results. So yeah, it's nice to see that you are producing a lot of these very nice, interesting measurements. I have a question about the stereo neutrino analysis, where you compare with Diabay. For your like kind of limits, are you still like statistically dominated? Do you expect this to be improving significantly with deploying more strings and or just analyzing more data? Or
I guess no. I mean, this is done using the Monte Carlo for the full ORCA detector. This is not ORCA 6 or 4. This is full ORCA.
Okay, I see. So this is like explicit.
Yeah. Yes, so here apparently Diabay still is mostly better than ORCA.
Yeah. So I mean, I think we will already on archive. You've got slightly better result, but you might still be slightly better in the low.
Yeah, of course, we might improve something in the analysis itself, etc. But for the detector, this already uses full Monte Carlo for the full detector.
I see. Very good. Yeah. Okay. Yeah. Thank you very much. Yeah. Thank you for the answer.
You're welcome. Thanks for the question.
Any other questions? No. So in that case, let's move on. So next speaker is Patrick Stengel. He will talk about Paleo-Detectors for galactic supernova neutrinos.
Just share my screen.
Now we see your video. Now it's coming.
Okay, can everyone see?
Yes.
Okay. So today I'm going to be talking about a little bit of a different idea to look for galactic core collapse supernova using minerals that are several hundred million years old and have been buried a few kilometers deep in the Earth. So this is based on a talk or a paper from about a year ago. I also wanted to use this opportunity to advertise a paper we wrote about atmospheric neutrinos as well. That came out earlier this year. So one of the problems with looking for galactic core collapse supernova with conventional experiments is that they don't happen very often. So you only expect there to be 2 or 3 supernova 1987A events every 100 years or so. And so if you back out and you say, well, if I have 100 million years of exposure, then this turns into something a little more realistic to look for, in particular to measure some kind of rate. And if you can get multiple measurements from paleo-detectors of different ages, then you even have a chance of tracing the star formation history in the Milky Way, because on these sorts of 100 million year timescales, the core collapse supernova rate is similar to the star formation rate. And so just to give you an idea of the spectrum that we're looking for, you can see down here that the comparison to the diffuse supernova background in black, the galactic signal, again, backed out over long time scales, is in red. You can see that the normalization is a couple of orders of magnitude higher because of flux. The sources are closer. Also, the energy is a little bit higher because you're not redshifting neutrinos. And the way we look for these tracks is using transmission electron microscopy. And you can see in these sort of pretty pictures, ions basically flying into or out of various materials. And you'll notice next to sort of the normally ordered lattice of whatever material you're looking at, the tracks are sort of these amorphous pieces. And so the idea about how these tracks form is not super well understood, but we have a pretty good qualitative picture, which is that your recoiling nucleus comes from your neutrino interaction, and that nucleus goes through your crystalline lattice and ionizes atoms along the way. And then if you have not very conducting material, Coulomb repulsion will basically push these guys all apart. And that's how you wind up with this amorphous track. That picture also lends itself to a fairly straightforward calculation of the track length in the material. Just integrating the stopping power along the track gives you something approximate to the track length. And so for a given nucleus that recoils off a galactic core collapse supernova neutrino in a given material, you can make a sort of one-to-one correspondence between the recoil energy and the track length. And the spatial resolutions of the techniques we're talking about are, in this talk, something like 15 nanometers or so for reading out the tracks. And then you can ask, what is this equivalent sort of recoil energy threshold in a given material? And so if you take 15 nanometer spatial resolution using small angle X-ray scattering at a synchrotron facility, that translates into a few keV nuclear recoil energy threshold, which is similar to next generation liquid xenon experiments. And so, like I said earlier, you have to pull these things out of the ground. In particular, you want them to be buried fairly deep in boreholes in order to avoid cosmogenic neutron backgrounds. The units and numbers are all a little bit different because the size of these things is not like a big tank of liquid noble gas. Also, the exposure time is longer, but in sort of the numbers that we care about, you can go down to about 5 or 6 kilometers, and you're left with 10 or some hundreds of cosmogenic neutron events. And I think it's important to point out at this point that this is one place where paleo-detectors are really different from conventional experiments, in that at the sensitivity threshold, you're expecting something like 10,000 signal events, and your radiogenic neutron background is also going to have a similar number of events. And so if you have a few hundred cosmogenic neutron events, it's not really going to impact your sensitivity at all. That being said, you need to make sure that you have the most radio pure materials possible. And so typically in the Earth's crust, uranium concentrations, for instance, are about parts per million or so. And there are some exceptions to that. Certain rocks that form in particularly radio pure environments, either from evaporated seawater, rocks called marine evaporites, or rocks from the mantle, which come from sort of deeper and then uplift. And so the radiogenic backgrounds that you look for, in particular the fast neutrons, come from the typical sources, right? Either spontaneous fission or alpha N interactions. And another difference between paleo-detectors and conventional experiments is that we don't have coincidence timing information, obviously. And so if you have multiple scattering events, you can't just reject them. And so you just have to count all of them in your background modeling and hope that the numbers don't get higher than whatever your signal sensitivity is. It also helps guide sort of the kind of materials and minerals you want to look for. In particular, you want something that's hydrated, because then you can moderate the neutrons a bit more and try and keep this number of scatters down as low as possible. Other backgrounds for this kind of search, I already mentioned the diffuse supernova background. There's obviously solar neutrinos down at lower energies, atmospheric neutrinos at higher energies, bracketing sort of our signal, which sits around here. And you just turn these into nuclear recoil spectra, and then those get turned into a track length spectrum, and you're left with overall fluxes in the track length spectra that look like these. So you'll notice that this is dRdx, again, in units that are different from what you might typically see, but what we care about. And this is a track length spectra rather than a recoil energy spectrum, because it's observed just the track lengths. But a lot of the features will be familiar, right? In particular, you can see that the blue galactic supernova signal is buried by the solar neutrinos at low energies and comes out over the atmospheric neutrinos out at higher track lengths or energies. Another thing you'll notice is the green line, which is the radiogenic neutron background, is really, really large, right? And even for these very low uranium concentrations, the overall flux can be very, very high because your exposure is so large. And you can also see that the kind of mineral that you're working with becomes important. So halite and epsomite are similar, and you can find them in similarly low uranium concentrations. However, epsomite has water in it, and this significantly reduces the radiogenic neutron flux by several orders of magnitude. And so if you have something like a hydrated marine evaporite, epsomite, then it just becomes a matter of, are your systematics good enough on your radiogenic backgrounds in order to detect this signal, which is still sort of 1% of the total flux, right? So you need about percent level control of your radiogenic systematics. However, we think this sort of control is achievable because when you can sort of calibrate these interactions just by putting a radiogenic source next to one of these materials to get an idea of what the spectrum should look like. And also keep in mind that you have a spectrum. You're not just looking at several events. And so in particular, you can do some spectral analysis where you can use these super long track length regions in the radiogenic background as a control region, and then use that to control your systematics more in the signal region down at a few hundred nanometers where the galactic supernova signal is strongest. The systematics for the neutrino backgrounds are a little bit harder, in particular because the neutrino rate is actually, of course, expected to change as some function of time. And so in our background modeling, we assume just an order 1 uncertainty in the atmospheric neutrino background. So putting all of that together, you wind up with a picture like this one. You can ask, what's the minimal detectable galactic core collapse supernova rate in a target with a given mass of a given age as a function of uranium concentration? So the gray dashed lines are sort of these 2 or 3 per century rate targets. So this is assuming you have a constant rate and how sensitive you could be to that. The different colored lines are different minerals. I showed the blue line epsomite on the previous slide in the track length spectra, but you can see here as the uranium concentration gets down to 0.01 or so parts per billion, you could become sensitive to the kind of supernova rate that you expect to see in the galaxy. You can also turn the question around a little bit and say, if I fix the uranium concentrations, how old does the mineral actually have to be? And again, with an epsomite detector, you can sort of see you don't actually need it to be 1 billion years old, just a few 100 million is fine. And going much longer than that doesn't really help you very much. And the last thing we did in this paper was you can also look for some sort of constant time evolution and compare that to just sort of a null hypothesis of a flat rate. You can also look for starburst events in the galaxy. And so these plots are showing the minimal detectable number of core collapse supernova in a starburst event at a distance of 10, normalized to a distance of 10 kiloparsecs away. For various uranium concentrations with a series of paleo-detectors that are 100 million years apart. And you can translate that into some picture of what you might look for in the galactic center or in the large Majorana clouds. And basically for parameters corresponding to what you might expect for a starburst event, our sensitivity is given by these colored lines. And so if there is something that happened in, say, galactic center, there's a chance we might be sensitive to it. There's obviously a lot of blanks to fill in here for the feasibility of this type of experiment. In particular, these sort of 0th order approximations we've done for the geology are okay for sensitivity projections, although we can argue about them. But to do an actual experiment, you really have to model the geology a good bit better. Also, like I said, you need to have very, very radio pure materials. We've been doing some preliminary mass spec on some sort of prototypical targets, and we're sort of getting below the blank level on the particular mass spec instruments that we're using, which is about 0.1 parts per billion. So of course there's some distribution and you want to just have the lower part of that distribution, but results are so far positive. And also the last thing we have to do is just sort of determine how efficiently we can reconstruct these tracks and read them out, and how quickly we can do that. Because basically all of the exposure, because the exposure time is so long, the limit to the exposure will just come from how much material you're able to read out. As I mentioned at the beginning of the talk, we also have a paper recently about atmospheric neutrinos, and there's a few papers out as well about using paleo-detectors to look for dark matter signals. Okay, that's all. Thank you.
Thank you very much. The session is open for questions. Any question? I see no. Then, okay. Eric, again.
Yeah, I'm sorry. I again have some questions. Yeah, thanks for a very interesting talk. I have maybe 2 questions.
Yeah.
Are you sensitive for diffuse supernova background, or this is buried under some other background, like
right. So it's buried under the galactic signal that we're actually looking for, right? So if we go back to this slide, right? So if you think about it, because the sources are closer, the flux goes like 1 over d squared. If the low rate is no longer a problem because of the long exposure time, the galactic signal will always just be much larger than the diffuse one.
But if I understand that correctly, galactic one is just, just like one and then nothing. While the diffuse supernova background, I mean, it's diffuse. I mean, it's accumulated over time, right? Or so my
Yeah.
idea is, okay, if I drill the mineral from certain age, I might be lucky to see the like galactic supernova explosion at that I don't know time.
Yeah, so I think it's basically that. So star formation peaks at around a redshift of 1, right, or 2 or something, right? And so typically that means that you're only sorry, if you're only sensitive to current time, right? That means that your diffuse signal will always be larger than your galactic signal. However, if you assume some sort of peak in the galactic supernova rate at the same sort of redshift that you actually have access to and can measure, right? Then you're sort of putting the rates on equal footing, and it's just a matter of flux largely at that point. Does that make sense?
Yeah, okay, yeah, thank you. Maybe if I may, one more question. How much, do you have estimation how much samples do you need to like analyze? I mean, is it how many boreholes and how many material do you really have to excavate to get some answers? Like,
right.
Is it,
so
is it tons or yeah?
Yeah. So obviously drilling boreholes can be expensive, and we haven't completely gone into like writing a white paper for the feasibility of paleo-detectors. We've just been building the science case, given that there are many active boreholes that contain the kind of minerals that we're looking for, that you could potentially get some samples from without having to dig your own. The question about how much material you need, I mean, you just don't need very much, right? So I was talking about like 100 grams of total sample materials for an individual paleo detector. Because if you think about it, right, these are just, you're really, like the scales are just so small, right? The tracks are some 100 nanometers long. And so you're really looking at individual like crystal grains containing a lot of information, right? And so it's not so much that getting the amount of material is the problem. It's getting the kind of materials that you want. And we haven't done sort of we have some preliminary idea of the availability of these materials, but it would really take a dedicated sort of white paper or something really to work out the precise. Obviously, you're not going to just like dig up the right rock right away, of course, right? So that sort of study we haven't quite done yet, but we know at the very least that these materials seem fairly reasonably available. We just have to talk to geologists and people who are experts in this sort of thing a bit more to get a better idea.
Okay, yeah.
All right.
Thank you very much for the answers and for the
Let's
talk.
move on. Thank you very much. So next is sufficient and necessary conditions for CP conservation with Majorana neutrinos by Professor Shun Zhou. Please.
Hello, can you hear me?
Yes.
Can you see my screen?
Yes.
Okay, good. Okay, thanks a lot. Let us shift a little bit to this neutrino theory. So today I'm gonna talk about the sufficient and necessary conditions for CP conservation with 3 massive Majorana neutrinos. My talk will be based on a recent work in collaboration with one of my students, Binrong Yu, and this work was published in Physics Letters B this year. So first of all, I want to motivate a little bit why CP violation is interesting and important. First of all, we have this CP violation is one of 3 necessary conditions to dynamically generate the antimatter asymmetry in our universe, as proposed by Sakharov in 1967. On the other hand, CP violation has already been discovered in the quark sector and is naturally expected in the lepton sector as well. So you can see this latest review about flavor physics for neutrinos and quarks by Professor Shin. And the latest experimental results from T2K collaboration, as shown in the left-hand side figure, there is about 2 sigma evidence for this leptonic CP violation. Of course, we need more data to establish this evidence for leptonic CP violation. Anyway, so how does the CP violation arise in the lepton sector? We have to extend the standard model by massive neutrinos. For example, we extend the standard model by 3 Majorana neutrinos, and the lepton mass matrix, here is the charge lepton mass matrix in blue, and this Majorana neutrino mass matrix in red. So all this lepton mass spectrum and the mixing angles and the CP violation can be effectively described by these 2 mass matrices. So at this moment, we are working in the flavor basis where the charge current interaction for leptons is diagonal in 3 lepton flavors. Let us now transform into the mass basis in which all the leptons have definite masses. So in this basis, we will have this non-diagonal charge current interaction for charge leptons and the neutrinos. We have this so-called PMNS matrix V here in blue. In the standard parameterization of this mixing matrix, we will have 3 mixing angles and also 3 CP violating phases. The CP violation stems from this 3 non-trivial phases in the PMNS matrix V. So if we want to have CP conservation, there is one sufficient and necessary condition, that is this V mixing matrix is real. One can prove this by performing the CP transformation on the lepton and gauge fields. In this way, we change this charge lepton field into the charge conjugate, and of course, the parity transformation of this field. And similarly, we can do the same thing to the neutrino field and also the gauge boson W. One can see that in this way, this charge current interaction becomes on the right-hand side of this arrow, so which is identical to the Hermitian conjugate of the original term. But in the original term, you will have this the complex conjugate of the matrix element of the mixing matrix. If we identify these 2 terms, you will get CP conservation requires all these CP violating phases in the mixing matrix to be vanishing or physically trivial. However, as we know that for a given neutrino mass model, we have to specify the Yukawa couplings for leptons or equivalently the lepton mass matrices. After diagonalizing the mass matrices, you will get the masses of leptons and also the mixing matrix. If we require the mass matrices for leptons to be real, of course, there is no doubt that there is no CP violation in the theory. However, this is not a sufficient, this is sufficient but not necessary condition, because ML and MNu are not necessarily to be real. For example, if we rotate the lepton doublets in the flavor basis by a unitary matrix U, and we have to diagonalize this new mass matrices, M prime. So the M prime is related to M by the unitary matrix U. Of course, even if original mass matrices are real, you will get this complex mass matrices, M prime. However, the mixing matrix is not changed by this same rotation matrix U in the charged lepton sector and the neutrino sector. So one question is, what are the sufficient and necessary conditions for CP conservation in an arbitrary flavor basis? We want to emphasize that we are interested in CP violation, but we are talking about CP conservation. So what's the connection between CP conservation and CP violation? The logic is like this. Any deviations from the sufficient and necessary conditions for CP conservation will imply CP violation. That's why we want to establish this sufficient and necessary conditions for CP conservation. In the model building, you have to destroy these conditions to have CP violation. For this purpose, we follow the approach of a so-called weak basis invariance introduced by Branco and his collaborators in 1986 for the lepton sector. The idea is that we can generalize the CP transformation to include the transformation in the flavor basis. For example, for the lepton-handed fields, we have this unitary matrix UL for the charged lepton fields and neutrino fields. And also we have a UR for the right-handed charged fields. And the same for the gauge boson, which has only CP transformation. There is no flavor. So under these transformations, you can prove that the theory is invariant if the following two identities are satisfied. This is for neutrino mass matrix. The transformation will change mu into minus mu star. And for the charged lepton mass matrix, you will have this transformation which can change ml to ml star. But this is not convenient for our construction for the weak basis invariance. So we introduce this H matrix, which is the mass matrix multiplied by its Hermitian conjugate. So we have three such Hermitian mass matrices, so HL, H nu, and GL nu. The transformation rules for these new matrices are very simple. We can use this UL matrix to transform H matrix to its complex conjugate. All these three transformations are equivalent to the original one. So with these transformations, we can construct an infinite series of weak basis invariants like this I, A, B, C, and D, E, F. So this is a product of several matrices, like this HL to the power of A, H nu to the power of B, and GL nu to the power of C, and etc. For this kind of product, you will have very simple transformation, and the generalized CP transformation is just take this product to its complex conjugate. So to remove this flavor basis rotation matrix UL, we can take the trace of this product. And because the condition is to have its complex conjugate, if this satisfied this transformation rules, that means the imaginary part of the trace of the product of this matrix should be vanishing. So the CP conservation is equivalent to a series of weak basis invariants which are vanishing. This has been discussed in the literature extensively. So in the paper by Branco and his collaborators, 4 weak basis invariants were proposed to guarantee CP conservation in the lepton sector. But there is one question. We have 3 physical phases in the lepton sector, CP violating phases. Why do we need 4 conditions to guarantee CP conservation? In fact, there is a minimal set of 3 conditions, which was proposed by Reiner et al. In 2007. We have this kind of 3 conditions, but we can show that these three conditions are not sufficient for leptonic CP conservation. The calculation is very easy. We take this standard parameterization of the mixing matrix, and also we can calculate the invariance in any flavor basis, as we have already demonstrated that these weak basis invariants are independent of basis. So we can calculate I1, which is proportional to the Yaskov invariant. So if I1 is 0, we will get delta is equal to 0 or pi. Now we come to the other two identities, I2 and I3. If we require them to be vanishing, you will have two identities. Naively, we will expect that the solutions to these two identities will give us trivial CP violating phases rho and sigma, but this is not true. We can find other solutions. Even these conditions are satisfied, we can have a non-trivial rho and sigma. This can be only done in a numerical way, because F and G are very complicated functions of all 6 lepton masses and 3 mixing angles. In these two plots, we show that if M1, the lightest neutrino mass, which is only parameter not yet determined by neutrino oscillation experiments. So if M1 is smaller than M star, here M star is around 0.0265 electrovolt, we cannot find any non-trivial solutions to these two identities. If M1 is larger than M star, you can see the real parts of rho and sigma are non-trivial, and the imaginary parts are 0. That means rho and sigma can be non-trivial solutions to the two identities. What does it mean? It means that if M1 is below M star, these three conditions serve as sufficient and necessary conditions for CP conservation. But if it's not the case, we will have non-trivial solutions for rho and sigma, which means CP violation. Of course, we can shift this M star critical mass for this lightest neutrino mass to a larger value. For example, we choose a different set of weak basis invariants, I1, I2 hat, and I3 hat. We can get this critical mass to be 0.142 electrovolt. That's large enough for these three conditions to be sufficient and necessary conditions for CP conservation in the lepton sector. Okay, and let me summarize. We have re-examined sufficient and necessary conditions for leptonic CP violation with Majorana neutrinos. The number of minimal set of conditions depends actually on the yet unknown lightest neutrino mass, M1. Of course, we assume that the normal neutrino mass ordering is the case. We give a new set of conditions for CP conservation for M1 smaller than 0.14 electrovolt, which is not enough given the cosmological bound on the sum of 3 neutrino masses. We also prove that in our paper, we don't show any details here. These 4 conditions are sufficient and necessary to guarantee leptonic CP conservation. I listed this in the red box. These conditions will be very useful for model building, for neutrino masses, flavor mixing, and also leptonic CP violation. Thanks a lot for your attention.
Thank you very much. We may accept short, quick question. Jason Singh, please.
Yes, can you hear me?
Yes.
So for these 4 conditions, if one of the neutrino masses is exactly vanishing, it can be reduced to 3.
Actually, it's not. If we calculate this invariance explicitly, you will see that they will depend on the mass square differences of neutrinos and also for charged leptons. So if one eigenvalue is vanishing, I think this doesn't change this invariant.
I see. Thank you.
Okay, thank you very much.
Thank you.
Then let's move on.
Okay, thanks. Okay, thanks a lot.
Next is Electromagnetic Neutrino Properties, New Constraints and New Effects by Alexander Studenikin. Alexander?
Yeah, good morning, everybody. Do you hear me?
Yes.
Hello, do you hear me?
Yes.
Вань, помоги мне, пожалуйста.
So I have to switch my screen.
Подойди, пожалуйста, сюда, Вань, я в эфире, Вань.
Ну, тебя не видит никто, Вань. Okay. Do you hear me?
Yes.
Yeah. Okay. Is it okay? Это брать как? Ага. Okay. Алло, do you hear me?
Yes. Please go
Yeah.
ahead.
Yeah, thank you. Thank you very much. Well, it is a really pleasure for me to have this chance to present a wide, or rather short in time, review on neutrino electromagnetic properties. I will fix your attention on some important constraints on the most important neutrino electromagnetic characteristics. I will try to add some new material in this field, since our big review paper with Carlo Giunti on neutrino electromagnetic interactions, a window to new physics, was published a couple of years ago. And also in the final part, I will discuss some new effects in neutrino electromagnetic interactions, in particular some new three phenomena in neutrino spin flavor, and flavor oscillations in moving matter and magnetic fields that are related to neutrino electromagnetic properties. So there is no doubt that neutrino is a massive particle, and just straightforward that even in the easiest generalization of the Stern model, at least the magnetic moment shouldn't be zero. And if we put some numbers, estimations for acceptable mass of neutrino, we shall get a tiny value 3×10⁻⁹ Bohr magnetron. This is a tiny value in respect to the present constraints on neutrino magnetic moment that comes from astrophysics, that is 3×10⁻12, and also from the terrestrial experiments, JEMMA, this is anti-neutrino reactor experiment, and also the Baruchino data set the limit on 10⁻11 Bohr magnetrons. So just a few words about the theory of electromagnetic interactions. All information is confined in the electromagnetic vector function, which can be constrained by some theoretical reasoning, and the vector function in general can be can be expressed in four form factors that are electric, dipole, magnetic, and electric, and anapole form factors. What is important here that really Dirac and Majorana neutrino exhibit quite different electromagnetic properties. For instance, the Majorana neutrino can't have diagonal magnetic moments. Only the off-diagonal magnetic moments Majorana neutrino can have. So this is a decomposition of the most general decomposition of the form factors. Note that the form factors are matrices in neutrino mass eigenstate space. So the most understandable and widely discussed and investigated, of course, is the magnetic moment of neutrino. In the terrestrial experiments, the studies of neutrino electron scattering provide the most sensitive method for investigation or constraining magnetic moment. So the cross section it depends. This can be split on the standard model contribution and electromagnetic contribution that is proportional to the effective magnetic moment squared. And here is a plot showing the behavior of these two terms in the cross section as a function of electron recall energy. This is the flat dotted line stands for the standard model contribution. This colored line stands for electromagnetic due to non-zero magnetic moment contributions for different values of neutrino magnetic moment, 10 to minus 11, 3, 4, 5. So the lower the measured electron recall energy is, the more sensitive these kind of experiments are to the magnetic moments of neutrinos. And this is the best terrestrial experimental limit obtained by JEMA. This is a joint venture of Dubna and ICHEP. They use the flux of the Kalinin nuclear power plant, and the limit is 2.910 to minus 11. And now the new set of experiments are on the way, and in a few years, this experiment called JEMA-3 new GEN will be sensitive to the value of 5 to 9, 10 to minus 12 Bohr magnetrons. So Baruch-Sina 3 years ago, published new results from these solar neutrino fluxes, and this is 2.8 10 to minus 11 Bohr magnetrons. This is a summary of the existing constraints on neutrino magnetic moments. And now I would like to say a few words about another very important characteristics of electromagnetic characteristics, the charge radio. So in our comprehensive analysis performed together with Konstantin Kuzakov recently, we have shown in particular that the neutrino charge radius in neutrino electron scattering cannot be considered, as people used to do, by simply a shift of the vector coupling, but there are also contributions from flavor transition charge radio. And this idea was implemented within the China, Italian, Russian collaboration. And we investigated this issue using the coherent experiment data and put very severe bounds on the charge radio, including the first bounds on the transition charge radio. So these results were highlighted by the editors of PhysRevD, and also these constraints were included to the review of particle properties by the particle data group. So this is the summary of the existing constraints on charge radio. And I would like to recall that indeed the coherent neutrino scattering provide very severe constraints on many other fundamental properties of particles, and including the neutrino transition magnetic moments. In fact, it is not excluded that neutrino can be merely charged particle. So, and there are a lot of attempts to constrain neutrino merely charge from different experiments, but the most severe constraint comes from neutrality of hydrogen atom. This is 310 to minus 21 if measured in charge of electron. So some years ago, I examined the JEMA collaboration data of reactor antineutrino cross-section and added additional term that might appear due to possible merely charged neutrino interaction with electrons, and set a bound, obtain a bound on the level 1.5 10 to minus 12 for the merely charge of neutrino. This bound also included in the by the particle data group to the neutrino properties. And it is expected, and we predict that after a new experiment, JEMA and new GEM will obtain data in a few years. This experiment will be sensitive to the merely charge of neutrino on the level 10 to minus 13. So here are illustrations on the most important electromagnetic interactions that can appear due to non-trivial neutrino electromagnetic properties, like the neutrino decay, Cherenkov radiation, plasma decay, neutrino scattering on electron or nuclei, neutrino spin precession on external electromagnetic field or the source. So these processes enable us to obtain astrophysical bounds on neutrino magnetic moments, for instance, using the supernova neutrino fluxes. And due to the fact that in the magnetic moment scattering, there is a change of helicity, and considering the energy deposit, we can constrain the magnetic moment of neutrino on the level of 10 to minus 12. So there are, as I mentioned, there is a bound from red giant stars. There is 310 to minus 12. This is the most severe and is the most important, people used to say, astrophysical bound on neutrino magnetic moment. And now I would like to turn to the most severe bound on neutrino merely charge from astrophysics. Recently, we have considered neutrino propagation in environment with magnetic fields and rotating media, and have found that the energy is quantized not only due to merely charged neutrino interaction with the magnetic field, but also due to rotation, interaction with rotating media. And in the quasi-classical treatment of this phenomena, I have generalized the Lorentz force, electromagnetic Lorentz force, and include also terms that can appear due to weak interaction of neutrinos with rotating media and media with the change of density. And just impact of this Lorentz force enable us to determine or just introduce the so-called neutrino star turning mechanism. So the point is that escaping merely charged neutrinos move on curved orbits inside the magnetized rotating stars, and the feedback or effective Lorentz force should affect initial star rotation. And new astrophysical constraint on neutrino merely charge can be obtained from the demand to avoid the contradiction of the neutrino star turning mechanism impact with observational data on pulsars. And we get the bound on the level 1, 3, 10 to minus 19. That is the best astrophysical bound for neutrino merely charge. So there are some bounds from different astrophysical considerations. Now I would like to flash on our main recent results on neutrino spin flavor oscillations in moving media. So this is the history of the whole story of the neutrino mixing and oscillations. And till my papers 2004, it was supposed and believed that neutrino spin flavor oscillations can proceed only when magnetic moment of neutrino interacts with transversal magnetic field. In my paper, I advertised and introduced a new phenomena. In particular, it is the possibility to neutrino spin oscillations owing to neutrino interactions with matter under the condition that there exists non-zero transverse current component of matter polarization. And this is the most important result of this paper. So far, before this paper, it was supposed that neutrino spin oscillations may arise only in the case where there exists a non-zero transverse magnetic field in the neutrino rest frame. So I calculated the probability of neutrino spin flavor oscillations due to transversal matter current without need for any magnetic moment or any external magnetic field. So, and this effect has been confirmed independently by other people recently. And with my postgraduate student, we developed the quantum treatment of this phenomena. We considered neutrino flavors and helicity states accounting for matter, effect of matter motion in the presence of magnetic field, also including standard and non-standard interactions, and consider different varieties of neutrino spin flavor oscillations due to transversal magnetic currents, and investigate several important applications, and have found that this effect might have some link to real situations in astrophysics. So now this is the last point, and the neutrino flavor spin flavor oscillations in a constant magnetic field, and we have found that it is not possible to separate these phenomena as people used to do before. we instead of the helicity states, we use the stationary states of neutrinos in magnetic field. Helicity states are not stationary if magnetic field is present, and derive the probability, for instance, for the flavor neutrino oscillations, and have found that amplitude of flavor oscillations on a vacuum frequency is modulated by the magnetic field frequency. So, the point is that the discovered correspondence between the flavor and spin flavor oscillations in the presence of magnetic field can be important in studies of neutrino propagation in different astrophysical environments where magnetic field is present. So, and finally, we generalize these correspondence between spin and spin flavor oscillations to the case when neutrino is propagating in media with longitudinal and transversal currents. So transversal current acts as a transversal magnetic field and can induce the spin oscillations. And we obtain that the probability of flavor oscillations in presence of longitudinal and transversal matter currents is modulated by two matter frequencies that depends on the matter transversal current. So this phenomena should be also counted when people consider complicated environments with complicated motion of media. So my conclusions, this is a summary of what is known about neutrino electromagnetic properties, the difference between Dirac and Majorana neutrinos. This is the prediction of the easiest generalization of the stellar model, 3 × 10⁻⁹ if we take the mass about 1 eV. So what is important that much greater values than this standard model prediction can be derived in different theories beyond
we
their
are
model.
running out of time. So
yeah, so and this is the future prospect. So we expect that new gamma 3, new GAN, and probably Berexina will give new constraints. So just very recent, Xenon published new results of excess of electronic recall events, which can be interpreted as the confirmation of rather big non-zero magnetic moment of neutrinos. And in our recent paper, we proposed a new setup for observing the coherent electron elastic neutrino atom scattering. And within this approach, we predict that it will be possible to test the magnetic moment on the level 7 minus 10 to minus 13. So, and this is our posters that available on this conference. And I would like to invite people interested in electromagnetic properties to see some details. Thank you very much.
Thank you very much. But unfortunately, we are a bit behind the schedule, so let's move on. So next talk is about neutrino oscillation in dense matter, given by Professor Shun Zhou.
Sorry, I cannot share my screen for. Hello.
Hello, I can hear you. So Alexander, could you stop sharing?
Okay.
The screen.
Okay. Okay.
Yeah, thank you.
Okay, now we can see your slide.
Can you see my slides?
Yes, please.
Okay, thank you. My name is Shun Zhou from Xiamen University, and my talk today is about well-known matter effect, but in the dense matter. And the talk is based on recent work of us, at least here. So let's just begin with the matter effect. It's well known that when neutrinos pass through a medium, they may interact with the background particles and therefore more or less change the oscillation behaviors. Here is the effective Hamiltonian in the flavor basis, and which describe the propagation of neutrinos in matter, and it the first term is just vacuum Hamiltonian, and second is the matter potential, which describe the charge current and the inertial current interactions of neutrino with the matter. Note that in the tree level, the inertial current potentials are equal for nu e, nu mu, and nu tau, and therefore it just contributes a common phase to the neutrino oscillation, and therefore it's relevant to the neutrino oscillation. Only the charge current potential is important to the neutrino oscillation in matter. And also for antineutrinos, we have to change the signs of all these mass potentials. So let's put the diagonal terms aside, and then we can rewrite the effective Hamiltonian also in the flavor basis like this. And now we can clearly see that the matter effect is actually the interplay of these two terms, the vacuum terms and the matter terms. The first vacuum terms is determined by these two mass squared difference and the mixing matrix, and the second is the matter terms, which is on just there's only one element. I call it the matter parameters, which is defined by 2 times the neutrino energy and multiplied by the matter potential. And you can see that the matter parameter ACC is actually has the same unit with the mass square difference, so it can very easily compared with this at least 2 mass square difference. And according to the relative magnitude of these two terms, the matter effect in varieties of neutrino oscillation experiments roughly fall into these 3 different scenarios. If the matter parameters is much smaller than the 2 mass squared difference, then it's the vacuum term dominated. And if these 2 terms are comparable, and there is the neutrino oscillation may experience some resonance. In the standard 3 neutrino picture, there is 2 possible resonance, which we usually call it Stolen resonance and atmospheric resonance. And as the increase of ACC, the matter term will eventually dominate over the vacuum term. And here we came to the matter dominated case. Actually, the matter-dominated cases is less discussed, maybe because the energy of neutrinos, the high energy of a neutrino and or high density of the matter is required for this condition to be fulfilled, and it's not achievable by current neutrino oscillation experiments. However, in this talk, I will show you what's the neutrino oscillation behavior will be in this matter-dominated region. So in order to calculate the neutrino oscillation probabilities, one may first work out the effective neutrino masses and mixing by diagonalize this effective Hamiltonian. And then we can simply write down the neutrino oscillation probabilities in matter by replacing the neutrino masses and mixing in vacuum with the effective neutrino masses and mixing in matter. So in the case we're discussing where the matter turns dominated, as the increase of ACC, these 2 dimensionless parameters are approaching 0. So we can treat these 2 parameters as small parameters and diagonalize the effective Hamiltonian using perturbative series. Here, I just show the results, and all those terms proportional to these 2 small parameters are neglected. So here is the 3 effective neutrino masses. Actually, is the squared masses. So you can see that M1 squared, the effective masses, are much larger than the other 2 mass, and there's M2 and M3, the other 2 mass eigenstands are nearly degenerate. This result is understandable because in the matter-dominated cases, the matter turns dominates over the vacuum turn. So the vacuum turn just play a role as a small correction to the matter turn. So these 2 eigenstates should be nearly degenerate, and both of these 2 has a strong hierarchy with the 3rd eigenstates. So in the same time, the effective mixing matrix evolves towards a 2-flavor mixing matrix, and it can be parameterized just using simply 1 parameters. And we show the expression of tangent to theta tilde here, and you can see that the theta tilde is independent of the matter parameter. It can fully determined by the vacuum neutrino masses and mixing parameters. So here is the feature. Here's the figure shows the evolution of 3 squared effective neutrino masses as the increase of ACC. And here the arrows shows the direction where the matter parameters increase, and the right side with the red lines is for neutrinos, and the left side with blue lines is for antineutrinos. And one can clearly figure out the different regions where in the middle is vacuum dominated, and here is matter dominated, and one can easily figure out where the possible resonance region is. And I would like also to mention that actually for different mass ordering cases, the resonance neutrino or antineutrino may experience different resonance. For the atmospheric resonance, the cases in the normal mass ordering, neutrinos oscillation will experience atmospheric resonance. But in the inverted mass ordering, the antineutrino oscillation will experience the atmospheric resonance. So here is the effective mixing matrix elements, how these elements evolves with the change of ACC, and we can clearly see that here is the vacuum dominated region, and it slowly deviates from its vacuum volume, and when it enters the resonance region, it will dramatically change, and then here enters the matter dominated region, then it will quickly evolve to the value we given in this equations. Okay. So that's the effective masses and mixing parameters. But for neutrino oscillation probabilities, we also give the approximate expressions here. You can clearly see that the result is consistent with the effective masses and the mixing picture we have drawn. So we can find that the electron neutrinos is decoupled due to the very intense charge current in potential, and there is a remaining oscillation between nu mu and nu tau, and it has simply the form of two flavor oscillation. Okay, here is a figure show how the neutrino oscillation probabilities vary with ACC. Here we choose L over V to be a fixed value. So in the vacuum dominated region, the oscillation probabilities will slowly change and then experience the resonance and then go to its fixed value in the matter-dominated region. So this is just a picture I want to show you where what the neutrino oscillation behavior will be in the matter-dominated region. There is good news that the neutrino oscillation picture in this matter-dominated region is very simple, and it's determined by just very few parameters. But the next question is, how can we carry on an experiment to see this kind of matter effect? So, and I have a very broad idea. How about we carry out a long baseline neutrino oscillation experiment on a white dwarf? Here is the properties of a typical white dwarf, and you can basically have a mass. It has a mass along the solar mass. So you can imagine you just press solar into a volume of our Earth, then it's a white dwarf. So the density of a white dwarf is very high, about 6 orders larger than our Earth matter. So in this case, it's possible to have a significant matter effect, and that's not the only reason I choose such kind of experiments. The reason I choose white dwarf also includes that the white dwarf, the internal of white dwarf no longer undergo any fusion reaction. Therefore, it doesn't radiate the large amount of neutrinos by itself, and not necessary to consider very complicated interaction inside this dead star, just simply matter effect. And we can we also calculated the approximate mean free path of neutrino inside the dwarf, and it depends on the neutrino energy. And if the neutrino energy is less than 10 MeV, then we find that the mean free path of neutrinos is larger than 9 × 10⁵ kilometer, which is much larger than the size of the white dwarf. So
Okay.
we can.
You're running out of time, so could you stop as soon as possible?
Yes. Okay. So I just skip it and show the results. So here is how the oscillation probability when the neutrino being passed through the white dwarf. Here is the 9 oscillation possibilities, and we can see the dashed line is the vacuum oscillation for comparison, and the red is for neutrino, and the blue line is for anti-neutrino. I want to draw attention here. Here is the significant slope here when the energy entered the resonance region, and then this is the same feature, but for in the inverted mass ordering cases. So if you can see that in this case there is a hump in the anti-neutrino cases. So if the presence or absence of the resonance hump can be observed, then we may tell the neutrino mass ordering. So let's just results of how when the neutrino being passes through white dwarf, but we cannot actually conduct such an experiment on a white dwarf. But this kind of long baseline neutrino oscillation experiment is actually happened anytime in our universe. So in the right up corner here is the gravitational lensing, which we are familiar with. When the line goes through a galaxy dense object, then the line will be bent by this large amount of masses. So here, actually, we are now observe. Okay, how to say? So when the neutrinos travel from its source to the Earth, and it happened there is some compact object sitting between. So as we just showed, the oscillation probabilities may be changed due to the intense matter effect. So this effect on neutrino oscillation probabilities will finally embodied in the neutrino spectrum, which so we can say that the neutrino spectrum may be discharged by this kind of compact object, which is very like the gravitational lensing. We can regard it as a weak lensing. Okay, as I said, this is a very broad idea. So before we can finally say if this kind of effect can be really observed, there's a lot of details need to be studied, as I listed here. But I want to say that this effect could open a new weak window to uncover some hidden compact objects around us. So still worth to have more efforts on it. Okay, I think that's all for my talks. Thank you.
Thank you very much. Sorry, we don't have time for questions. Actually, we have already eaten up all the coffee break time. So please go to the next talk. Next is by Dr. Atri Bhattacharya. He will talk about perturbative charm production and prompt atmospheric neutron flux in light of RHIC and LHC. Please start.
Okay, I think you can hear me now.
Yes.
So thanks to the organizers for allowing me to present our work on perturbative charm production in the atmosphere and the consequences for prompt atmospheric neutrino fluxes. Most of what I'll present in this work is based on the work in 2015 that is referenced here in the bottom right corner. So briefly about neutrino production in the atmosphere. Cosmic rays coming to the Earth from distant sources interact with atmospheric nuclei, producing mesons of different kinds at energies of a few hundred GeVs to tens of TeVs. The dominant production of mesons are light mesons, pions and kaons, which then lose energy in the atmosphere before eventually decaying to form neutrinos. The neutrinos coming from this mode of production, from light kaons, is called the conventional atmospheric neutrino flux. Our focus in this particular talk will be on the prompt component, which is the neutrinos, atmospheric neutrinos produced from decays of heavier mesons, including charm mesons. So charm mesons are produced in the atmosphere at higher energies, and their decays are prompt in the sense that because of their shorter lifetimes, they decay to produce neutrinos before they have had the time to lose energies and interactions in the atmosphere. So the differences between conventional and prompt atmospheric fluxes are significant, not least to say that the conventional atmospheric neutrino flux has already been detected experimentally by Super Kamikande, for example, while and is also well understood theoretically, while both the theoretical understanding of prompt is beset with large uncertainties in the QCD modeling, and it is also a component of the atmospheric flux that hasn't been yet experimentally detected. So schematically speaking, at high energies, you have these important components of neutrino fluxes. There's the conventional atmospheric neutrino flux, which is expected to be dominant up to tens of TeVs in energy. And at the higher end, at the other end of the spectrum, one expects that neutrinos from astrophysical sources, which are modeled using simple power laws like e to the -2 or e to the -2.5, would take over, would become dominant. Nestled somewhere between these two extremes would be the prompt neutrino flux produced in the atmosphere from the decay of, from the production of charm mesons and their subsequent decay. So this typically happens at energies of around hundreds of TeVs and higher. So that's where the prompt flux would become an important component, would become either visible or an important background to extragalactic neutrino searches. So to understand prompt neutrino flux production, we'll retrace the production of a prompt neutrino from starting from the incident cosmic ray flux step by step. Right off the bat, there is a problem because incident cosmic ray fluxes that will produce the prompt neutrino flux at around TeV scale energies would require protons at energies of tens and hundreds of TeVs and higher. And the cosmic ray spectral shape and its composition are rather uncertain at energies of TeV, at energies greater than a TeV and tens of TeVs. So this uncertainty seeps into any calculation of the prompt neutrino flux that you are going to attempt. Once you take care of all the cosmic ray flux, you will have to take care of the QCD modeling, where a proton from the cosmic ray flux interacts with atmospheric nuclei, and produces a CC bar pair. Now, at very high energies, this process is gluon fusion dominated because it probes extremely low momentum fractions. So you can model the QCD, the QCD process in different ways. Supposing you choose to do it, in the paradigm of perturbative QCD, you'll have to determine what the appropriate perturbative order is for your calculation, and your calculation will be dependent on the theoretical parameters that you introduce, including factorization and renormalization scales. The quark mass itself has its own uncertainty, which will add to the uncertainty of your CC bar production cross-section. Once CC bar production happens, the CC bar pairs hadronize or fragment to form charm mesons. This is a non-perturbative process that is modeled in a few different ways. In the literature, the semi-analytic approach uses fragmentation functions, which convert differential cross-sections for charm pair production to differential cross-sections for hadron, the equivalent hadronic production. But event generators, for example, PTI use something called string models. There are other novel mechanisms to model this as well. All these different uncertainties in modeling the individual, the hadronization, the perturbative QCD, goes into the final prompt neutrino flux, which comes about from the decay of the charm meson produced in the previous step. This schematic program has been followed in existing literatures to estimate the prompt neutrino flux. I'll specifically point out two references here that have been influential in the literature. One, the first is by Enberg et al. In 2008, which used to be the ICECUBE's reference prompt flux estimate. So, this was a calculation based on a dipole model using leading order CTX6 PDFs for the high X distribution. But our analysis or our revision of the prompt neutrino flux will follow an older work by Pasquale et al. From 1999, which is a perturbative QCD. But first, let's address the question of why it is important to look at this, this problem now. And the answer comes from different directions. One is that our understanding of charm production in PP scattering itself is much improved because of recent collider experiments. So if you model the interaction, the proton scattering producing a CC bar pair interaction using perturbative QCD, there are stronger limits now on the factorization and renormalization scales that are enforced because of the because of constraints coming from high energy experiments, including RHIC at fixed target experiments, RHIC Star and Phoenix at around 200 GeV, and experiments from the LHC. Secondly, we also understand the cosmic ray fluxes at higher energies much better now, thanks to pioneering work, theoretical modeling work based on experimental results, updated experimental results from Pamela, Cream, Attic, and other experiments. So whereas previous estimates of the prompt neutrino flux used broken power laws to model the cosmic ray flux, we are going to use a Geiser model that is a composition of multiple sources of the cosmic rays. So these include supernova remnants at lower energies and some other galactic components at middle energies. And at higher energies, they're composed exclusively of extragalactic, of cosmic rays from extragalactic origins. And at higher energies, the composition of the extragalactic component is unknown. So it can vary between this green curve to this orange curve, where the orange curve represents an entirely proton-rich flux, whereas the green curve is more of a mixed, has a mixed composition. So heavy nuclei, protons, and others. And finally, but probably most topically, experiments are now looking at neutrinos, extraterrestrial neutrinos, extragalactic neutrinos, beyond tens of TeVs. For these experiments, Piotr talked about KM3net, which is sensitive to TeV plus neutrinos as well. For these experiments, it is important to understand the backgrounds. Atmospheric neutrino fluxes are backgrounds to these searches. And it's important to understand both the conventional and the prompt background in this context. So we go about improving existing prompt neutrino fluxes. And to do this, we look at it step by step. So firstly, we replace the existing, we update the existing QCD calculation by a full next to leading order calculation in the realm of perturbative QCD, using parameters that are consistent with charm production data. So we fix the charm mass at 1.27 GeV and allow the factorization and renormalization scales to vary as multiples of the transverse charm mass. We also use updated, more recent NLO PDFs for our calculation. I must note here that these are already superseded by CTEC 14 NLO PDFs, but we have swapped out one for the other and seen that our results do not significantly alter in any way. So our updated calculations will be indicated by this BERSS acronym, and it uses CTEC 10 NLO. And finally, we include the improved cosmic ray spectrum by Geiser et al. That I alluded to earlier. The full technical details of the calculation are complicated, but I'll highlight some specific features that are important in our calculation. So we use fragmentation functions to go from charm production differential cross-section to hadron production differential cross sections. And we use specifically the Neal-Kramers fragmentation functions described in this reference in 2006. To convert our fluxes first from proton flux to hadronic flux and then to the lepton fluxes, we use spectrum weighted Z moments. So these are dimensionless quantities that look complicated, but in essence, the ZPH multiplied by the proton flux will give you the hadron flux, and the hadron flux times the ZHL will give you the leptonic flux. That is roughly what it is. There are other, it's not exactly that, but that is the schematic picture of how this occurs. So put everything together and we arrive at our main result, which is the central reference prompt neutrino flux, which we obtain for the proton-rich cosmic ray incidence with best fit parameters for factorization and renormalization scale given by present experiments. So that's the red curve there, surrounded by its 1 sigma band of uncertainty. If you keep the QCD modeling identical, but swap out the proton-rich cosmic ray incidence in favor of mixed composition cosmic ray flux, so that's the H3A, our prompt neutrino fluxes drop slightly above tens of PeV or thereabouts. So the revised results are in contrast to the existing benchmark used in the literature. The ERS from 2008. And these are lower. Our results are lower by as much as a factor of 3 at PeV scale energies. So where does this leave the prompt neutrino flux with respect to current experiments looking at ultra high energy neutrinos? So it should be noted here that the conventional atmospheric neutrino flux dominates the prompt neutrino flux all the way up to a few hundreds of GeV, especially now that the revised estimates of the prompt fluxes are lower. And on the other hand, on the higher energy side of things, ICECube has already been indicating that it is seeing a large extraterrestrial, extragalactic component of neutrino fluxes that would swamp the prompt neutrino fluxes beyond a PeV or so. This reflects in the event rate calculation. So the revised prompt event rates stay safely below the conventional atmospheric background for IceCube data, for IceCube event rate calculations, wherever the atmospheric neutrino flux is significant. So we show a calculation here for, yeah, sure. Other related works have also looked at this problem, and there are interesting differences here, which I don't have the time to discuss in detail, but they have found fluxes that are largely consistent with ours. So the takeaway message here is that using a full envelope perturbative calculation with recent PDFs and updated cosmic ray estimates, we find that the prompt neutrino flux is reduced significantly compared to previous reference fluxes. At PeV scale energies, they're reduced almost by a factor of 3. In a related work, we also looked at the effect of shadowing in atmospheric nuclei, which further reduces this flux by about to the tune of 40% at around a PeV scale. And we also looked at the effect of different QCD modeling. So swap out the perturbative QCD modeling by a dipole model or a KT factorization and look at the changes there. I don't have time to go into this, but I would say that on the experimental side, there is a robust program under that IceCube is undertaking to infer upper limits on the prompt neutrino flux using different procedures that are relevant at these energies. So finally, I'll leave you with my summary, which is just this plot that shows our main result vis-a-vis all the other competing fluxes that are important at these energies. Thank you.
Thank you very much. Sorry, but again, we don't have time for question. So thank you very much. So next talk is neutrino mass ordering obscured by NSI by Dr. Sabya Sachi Chatterjee.
Can you hear me?
Yes, clearly.
Okay. So can you see my screen?
Yes.
Is it in?
I think it's large enough, so you don't have to.
It's large enough?
Yeah, now it works.
Okay, thank you very much. So thank you very much for giving me an opportunity to present my work here. So in this talk, I will discuss the impact of the neutrino non-standard interaction on the determination of the neutrino mass ordering, and this is based on this paper by Francesco Capozzi, myself, and Antonio Palazzo. So as you know that over the past few years, the tremendous efforts and the invaluable contribution from the neutrino experiments have established the three neutrino framework beyond any doubt. However, there might be some certain scenarios where the standard interpretation might not be the ultimate picture, and in that case, we need to invoke some new interpretation on top of the standard interpretation. And one of the most popular scenarios is the neutrino non-standard interactions, and which is very, very popular, and people have been working a lot for the last few years. So in this work, basically we will explore the impact of this non-standard interaction in the interpretation of current T2K nova data, and specifically focusing the neutrino mass ordering. So as we know that when M1, there are three light neutrinos, where M1 less than M2 less than M3, we call it normal ordering, and when M3 less than M1 less than M2, it's called inverted ordering. So now here it is worth to mention that the current global fits, including all the experimental data, that prefers basically normal ordering over the inverted ordering at around 3 sigma confidence level. So let me just briefly describe the current status of the three neutrino parameters with their 3 sigma uncertainties. And from this wheel, it is very clear that, as you know, theta 1, 2, theta 1, 3, and delta M21 square, which are known very precisely, quite precisely. And the two most unknown parameters is the theta 2, 3 and the leptonic CP phase delta CP, which is a long uncertainty, which is not confirmed yet as of yet. And the magnitude of delta M31 square, which is known, but the sign is basically unknown. It might be positive, it might be negative. For positive, we call it normal ordering. For negative, we call it inverted ordering. Okay. So now when you talk about the NSI, the effect of the effective 4 Fermi flavor changing neutral current non-standard interactions in the oscillation physics is basically realized through this well-known Lagrangian, where this epsilon alpha beta is a combination of the 3 terms, electron terms, and then up quark. There are 3 times plus 3 times the down quark terms, and this epsilon alpha beta might be also the complex, and these are the strength of the NSI parameters. So when you add when you add the effect of this NSI parameter, then the Hamiltonian actually changes like this with the extra matrix which is called VNSI, and VNSI is it's rescaled by the some parameters, which is some NSI parameters epsilon times the charge current matter potential VCC. And this plus and minus is for neutrino and anti-neutrino. Now it's in this work basically we have focused on the 2 non-diagonal parameters, which are basically epsilon E mu and epsilon E tau. So now when you in the presence of NSI, the transition probability is a very, very well-known equations. I'm not going to details. It's written by 3 terms, P0, P1, P2. And then there the new terms basically comes in u mu sector when you include epsilon e mu, that is P2, and then epsilon eta, this is again P2 with epsilon eta associated with phase phi eta, and for epsilon e mu there is also associated phase phi e mu, as these are the complex parameters. Okay, so as of the current constant, this is what I have quoted here from the from some references, and these are the constant given in 90% confidence level: epsilon e mu, epsilon e tau, and then epsilon meta, and then the difference between the diagonal terms. Okay, so in these works, basically we have considered the very the recent data. The data I am talking about, the data which is before presenting in the before which presented in the Neutrino 2020 and in this conference. So here these are the data set we have used for T2K 1 to 9, where 90 events for electron neutrino and 15 events for electron anti-neutrino, and for and 243 events for nu mu, and 140 events for nu mu bar for T2K experiment. And for NOVA experiments, we have used 58 events for electron neutrino, and then 27 events for electron anti-neutrino, and then 113 events for nu mu, and 102 events for nu mu bar. Okay, so in this slide we present our main result. So the upper panel, so this is a combined analysis of both the experiment T2K and NOVA, and this is the upper panel shows the standard mode analysis, where we have not considered any new physics scenario, as it is clear from the upper panels that the normal ordering is preferred over the inverted ordering at a 2.4 sigma confidence level. However, when you go to the new physics scenario, taking epsilon e tau one at a time, and in that case it is very clear that the preference of the ordering is basically is no more, and there is no sensitivity, only 0.7 sigma sensitivity. Also, it is worth to mention here that the octant sensitivity, if you see the upper panel, we can distinguish from the upper octant from the lower octant. I mean, sin square theta 2 3 equals to around the 0.45 by almost around 2 sigma confidence level. But when we include this NSI parameter epsilon e tau, in that case we see that the octant sensitivity also decreases because of the new degeneracy coming into the picture. Okay, and these results can be very easily understood by these bi-event plots. These are the bi-event plots. The left panel is for NOVA and the right panel is for T2K, where nu e and nu e bar events we have shown, and these ellipses are basically the where the running parameter is the delta Cp, and these ellipses are drawn from the best fit points obtained from the combined analysis of T2K NOVA, and this black dot is basically indicating the data point for each experiment. Now it is very clear, if you see the ellipses with the NSI, you can see that the squared, colored squared, blue and the red squared, which are almost at the same distance from the black dot point for both T2K experiment and NOVA experiment, and which basically indicates that the preference of the normal ordering and the inverted ordering basically goes vanishes, and there is no preference, only below 1 sigma point, only 0.7 sigma preference, as I have shown in the previous slide. So now these experiments are very unique experiments, this currently running experiment T2K NOVA, because this experiment also can constant the long baseline experiment. It can constant the new parameter associated with their phase also. They are very sensitive to the phase. So here we have shown the allowed region of the parameter. We have constant the parameter space, new parameter space. The left panel is for epsilon e tau and phi e tau for normal ordering, and the right panel is for inverted ordering. As we see from the star, red star, there's only 0.7 sigma preference for non-zero NSI for in case of normal ordering. However, it is basically for inverted ordering, it's a 2.5 sigma preference for the non-zero NSI with respect to the standard model case. It is important to note here that we have also checked, we have not seen the results for epsilon E mu, that the best fit value for epsilon E mu is 0.15 for normal ordering and 0.1 for inverted ordering. And in that case, most importantly, normal ordering is again preferred over the inverted ordering at 2.5 sigma confidence level. So the ordering, the preference of ordering actually vanishes in presence of epsilon E tau. So here we have shown the future sensitivity of DUNE. Suppose if the epsilon E tau remains around 0.2, and just we have shown here with 20% uncertainty, in that case, even we can see, even though the standard model sensitivity is very high, almost more than 10 sigma confidence for all the CP phases for DUNE, but in presence of epsilon E tau with that kind of strength, it can goes down even below 5 sigma confidence level. And if we if the CP phase is around minus 90 degree or so, then we can expect around 5 sigma confidence level. Otherwise, it can goes down below 5 sigma confidence level. So it is very. So let me conclude here that we have investigated the impact of the NSI on the current data of T2K nova, and we have shown that the indication towards the normal ordering in the standard model does not hold anymore in presence of the NSI of type epsilon E tau. However, the preference of normal ordering again is there over the inverted ordering at 2.5 sigma confidence level in presence of epsilon E mu. Also, we have shown that the sensitivity towards the resolution of the octant of theta 23 also goes to very low level. And we have also a very separate paper in DUNE also, we have shown a few years back this result. Now the very for the first time we showed this result a few months back, but recently there is new data presented in Neutrino 2020 and in this conference also, which actually makes the mass ordering sensitivity even more fragile in the standard framework without any new physics scenario, where the ordering preference is basically again it vanishes. Now it is, but we hope that this kind of ambiguity or this kind of degeneracy can be resolved with the long baseline experiments, like especially like DUNE, which has a huge high capability, and also the atmospheric current and future data like superchemicande. But in that case, we need to do an independent analysis of the super K data which is available. Currently, they provide the chi-square map for the standard 3 neutrino framework. But for new NSI, we need to do either we should get from the collaboration from within from the collaboration, or someone should do very independently. Or also I think that the importance of JUNO experiment actually plays a very crucial role in this case, because this experiment is very less sensitive to the standard and non-standard meta effects, and then in that case, which will be very useful, and it can clearly say something about the mass ordering, and that's it. Thank you for your attention.
Thank you very much, especially for keeping the time. Okay, we have time for 1 or 2 questions. Any questions for Sabya Sachi? I see no questions. In that case, please let me go on. Thank you very much.
Thank you very much. Thank you.
Okay, then the next talk is why metal effects are important for medium baseline experiments by Dr. Amir Khan.
Hello.
Hello.
Yeah, can you hear me?
Yes.
Okay. The screen is visible now?
Yes.
Okay, good. Okay. Hello to everyone, and thanks for the opportunity to present my work here. I will talk about why matter effects are important for these prospective measurements at medium baseline experiment and practice, of course, JUNO. And this is a collaboration work with Hiroshi Nunokawa and with Stephen Park. So there are two parts of my talk. In the first part, I will explain some the oscillation probability required for these such experiments and how the mixing parameters are affected by the matter effects in such experiments. In the second part, I will focus on the so-called shift issue, which is a disagreement between the expected and the fitted values on the solar parameters in these experiments. And then I will spend most of my time on the analytical check of this shift issue, whether they agree with the expected one or with the fitted values. So here is the oscillation probability look like it in any medium baseline reactor-based experiments. So there are two types of oscillation. One are these large oscillation, which are controlled by delta M21 and theta 12, the solar parameters, while small oscillations are driven by these atmospheric parameters, delta M31 and theta 13. So for the mass hierarchy measurement, it's it experiment like JUNO. These small oscillations are important, but for the precision measurement in these experiments, the large oscillations of the probabilities are more relevant. And we can see that that the large minima, which is due to the solar oscillation parameters, lie exactly at the peak of the reactor neutrino flux at between 2 to 4 MeV. So here is we can compare roughly the vacuum oscillation probability with the exact matter effect probability, and we can see that in the main region of interest, there are 3 to 4% matter effects for experiment like JUNO. So in order to correctly estimate the matter effects, both the probability and these mixing parameters, we derive oscillation probability formula for this purpose. In this, the result is given here, which is an exact analog of the vacuum probability, except for the mixing parameters, they are replaced by those with matter effects. And they are given here, these four. The two are the atmospheric, and the other two are the solar mixing parameters. And we obtain them. These are the, of course, these are the approximate expressions which we obtain from the exact expression and given in reference 3. And the expansion parameters are, of course, there are two expansion parameters. The first one is the ratio between the matter potential with the atmospheric effective mass square difference, and the second one is the ratio between the matter potential with the solar mass square difference. So here we use the expression up to first power A over delta ME square and up to second power in A over delta M21 square. And with these this much this order of the expansion parameters, we can get the accuracy of or probability more than required for the experiment like JUNO. So in order to get to have a feeling of how much accurate our calculations are, so we compare them again with the exact matter probability here. And this for the three different cases, the first one for those which we obtained is the main expression from which we derived our approximates one. So it is denoted by this DMP here, where approximate 1 and 2 corresponds to what order of the expansion parameter we consider here. So here are the effects on the explicitly on all mixing parameters. On the left top bottom shown here are simple ratio of the matter and vacuum, while on the right side is the fractional differences. And we can see that in the top right panel, we can see that the solar parameters have an order of magnitude more impact due to matter effects as compared to the atmospheric parameters. And this was already pointed out in my first slide. So, and how the matter effect affect the spectrum with full details of the detectors included. So here we can see for 5-year runs of JUNO, with 3% energy resolution of the detector, we can see at the main region of interest from 2 to 5 MeV. Again, there are around 3 to 4% matter effect. So now I will switch to this so-called shift issue, and we see that in the shift issue is we simulate our data with matter effects, and then fit the model with matter to the data, and then without data. So the first one case is given on the left-hand side, and in this case we have in this case we don't find any effect, while on the right-hand panel we can see that when the vacuum model is fitted with the data including matter effect, so the best fit point is shifted, which is shown in blue color. So the as we can see from the right-hand plot, that the matter effect preferred the smaller value for delta M21, while I prefer a larger value for theta 12. So what is the magnitude of these shifts? It's given here. So the percentage shift in the theta 12 is minus 1.1%, while delta M on the mass difference, it's around 0.2%. Now, in order to compare that with our estimation, our expected results is shown in the initial slides. So at the fixed energy of around 3 MeV, we can see that only the mixing parameter theta 12 agrees, while at 2 MeV, the mass square difference agrees, while at a single energy, a fixed single energy, none of these two parameters agrees with each other. And this is which I call the shift issue. So in order to explore further this shift issue, whether they disagree with the expectations or with the fitted values, we define a simple event number distribution here, both for the expected and for the data station. And this is the product of the event number without oscillation in 0E times the probability with matter effects. And the probability we split it into two parts, the vacuum dominated part plus the correction from matter here, while the vacuum probability we take is in a very simple form and average out all of the small oscillation shown here by a factor of 2, a factor of a half here in the last term. And while the matter corrections are expressed in terms of the shifts of delta sine squared 2 theta 12 and delta mass square difference 2, 1. So based on this structure, we define further our observed event energy spectrum, which is a product of the normalized expected number of events without oscillation times the sum of the vacuum and the matter corrections here. Now for the fitted model, we assume that there are no matter effects and it's purely vacuum oscillation probability. But the fitted parameter, that is the mixing angle theta 1, 2, and the mass square difference, we apply a shift of x and y, which are just dimensionless constant, and we see that what are the values of these x and y, whether they agree with the naive expectations or with the fitted values. So here is the explicit form of the fitted event energy spectrum, which is again a product of the same factors, except for the matter correction, which is now a function of x and y. So what is x and y? For this purpose, we define a simple chi-square, and without considering any details from the reactor or any systematics, it is based only on the statistical uncertainty. So, and we replace this n observed and n fitted by the expression shown before. And then we minimize this chi-square with respect to the two unknowns x and y. And this leads us to two linear coupled equations for the two unknowns x and y. While these the other coefficient a, b, c, d, and f, g, they are the expression when we expand the integrals in the chi-square shown before. So here these a, b, c, and d, they are fixed numbers when we solve these integrals, while f and g are the matter density dependent functions. It's shown here. So for the standard Earth matter density of 2.6 gram per cubic centimeter, and with a atmospheric mixing angle of 0.0214, we get the value of x and y is minus 0.32% and y is 0.20%. And if we translate them into the single angle, that is sine square theta 1, 2, to compare with our expectations or with the fitted values, so we get the result is minus 1.1 and 0.20%. And then now if we compare this with our previous result, for the one obtained from a full chi-square and then from the naive expectation, so we can see that they are in agreement with the chi-square, and they do not agree with the naive expectations as shown here. So summary on this shift issue, and it's also a kind of a proposal for the JUNO experiment, that the fitted value of the mixing parameter theta 1, 2 should be corrected with the second term here in the bracket, while for the mass square difference, it should be positively corrected with this term, where A, B, C, D, these constant we have computed as shown on the previous slides. So if we want to see the full chi-square results and the one obtained from the naive expectation, in the third case from the independent check, explained here. So we have shown it here. These data points correspond to the data points to the full chi-square analysis, and they are given here for three different values of density. The one for is the density, the true value of the matter density, and the fitted one is the same, and the red one is the one, the standard constant density profile, and the blue color one is the one for if we have a large density as compared to the standard one. While for the other two cases, for the expected and for this independent check, analytical check, we continuously vary the density. So again, we can see this magenta color, which is from the naive expectation, it does not agree with the data points even for a different density, for a slightly large density. While in the green color shown here is the one from this analytical method, and they agree well. So the important point here is this B with the standard constant density profile. And this is the point which also we have shown before. So here from this plot also, we can see that this shift issue is not depending on the varying density profile. So for constant density profile, or whether it is varying density profile of Earth matter, this issue is still there. So with this, I will conclude here. Yeah. So in this work, we derive simple oscillation probabilities and also the effects on the mixing parameters. And we find here the maximum matter effects occur at the solar minimum, and they are around 3 to 4%. And also, we have shown that there is a conflict between the full chi-square and the naive expectations. It is called the shift issue. And this shift issue was also checked independently, which agrees with the full chi-square. And what is the possible source of this issue? So it could have some connection with this 2 sigma mismatch on delta M21 from solar and Camlin measurements, as discussed by Mariam and the first day. Or they could be, the source could be some NSI or something else. We yet don't know about it. So I will conclude here. Thanks.
Thank you very much. Sorry again, we have no time for questions. Let me move on. So the next talk is new constraints on heavy neutral leptons coming from oscillation data analysis and precision E plus E minus physics by Wojciech Flieger. Please.
Okay, can you hear me?
Yes.
Yes, okay, thank you. So I will talk about the method of analyzing the neutrino mixing matrix, which will give us the prediction on bounds of the active sterile mixing. And this is based on the research we are doing together with Janusz Gluza and Kamil Porwit. Where can we look for the signals of sterile neutrinos? Of course, in the light neutrino oscillation, in the precise correction to the physical process, in direct production in colliders. Of course, this is not the end of the list because we have also cosmological observation. Below, I listed some review talks from Neutrino 2020 about the searches of sterile neutrinos. So here's the picture we all know. So the neutrino mixing in the standard model. So we have 3 flavor states neutrino and 3 massive states neutrino. They form 2 bases, and the transition between these bases is given by the unitary matrix known as the PMNS mixing matrix, which can be parameterized in the following way. From the oscillation experiment, we can extract the allowed ranges for the mixing parameters. And if we combine these 2 elements, we will get the all allowed ranges for the all elements of the neutrino mixing matrix. And if we forget for a second about the correlation between these elements, there is within this ranges, there is still a lot of place for the beyond standard model physics. In the presence of sterile neutrinos, the unitary matrix, the PMNS mixing matrix, is no longer unitary, but is a part of a larger unitary matrix in such a way that the mixing between 3 known neutrinos must be preserved. And the signals of such new neutrinos should be visible as the deviation from unitarity of this PMNS mixing matrix. And we are interested in the estimation of the active sterile mixing. This will be done in twofold ways. First, we will analyze the neutrino mixing matrix, and then we will look briefly at the potential of the Z boson decay in the searches for sterile signals of sterile neutrinos, which is very important for the future colliders because the statistic of such events will be very significant. So we wanted to think a little bit out of the box and look at the source of the problem, because the neutrino mixing matrix is, of course, the matrix. So we dig into the mathematical literature and look for the tools which could help us better understand the mixing phenomena. And we have found out that the quantities known as singular values and the procedure known as the unitary dilation are perfectly suited to describe mixing phenomena. So singular values are defined as the positive square roots of the eigenvalues of the Hermitian product of a given matrix. They can be treated as the generalization of eigenvalues to all type of matrices. They are also always positive, and they are stable under the perturbation, which is important from the numerical point of view, because we can estimate the error associated with singular values. Below, I present a simple example of the calculation of singular value for the unitary matrix. Of course, we know that the Hermitian product of the unitary matrix is the identity matrix. So from this, we concluded that all singular value for unitary matrices are equal to 1. Next, let me define the contractions, which are matrices with a spectral norm less or equal to 1, where this norm can be characterized by the larger singular value. Why is this important? Because if we recall that in the presence of the sterile neutrinos, the PMNS mixing matrix is no longer unitary, but is a part of a larger unitary matrix. And from the previous slide, we know that all singular values of unitary matrices are equal to 1. We concluded that all physical neutrino mixing matrices must be contractions. This allows us to define the region of physically admissible mixing matrices as the convex hull spanned on the 3-dimensional unitary matrices with parameters restricted by the experiment. However, singular values not only allows us to distinguish between physical and unphysical mixing matrices, but they also control the dimension of this extension to a complete unitary matrix of some beyond the standard model scenario. In other words, they control the minimal number of additional neutrino, and this number is not arbitrary, but it's encoded in the number of singular values strictly less than 1. These characteristics allows us to divide this region into 4 disjoint subsets, each corresponding to a different number of additional neutrinos. So by studying separately each of these subsets, we can expect a priori to obtain sharper bands for the active sterile mixing for each scenario. So to get the active sterile mixing, we use so-called unitary dilation, which take the 3-dimensional PMNS mixing matrix from the R region and put it into the larger unitary matrix, in such a way that the mixing between non-neutrinos is untouched. Numerically, this can be done by so-called cosine sign decomposition, which decomposes a given unitary block matrix into the following product, where the middle matrix and these 2 matrices are fixed by the singular value decomposition of the PMNS mixing matrix. We have focused so far on the 3+1 scenario, so the scenario with 1 additional neutrino, and we look at the structure of the CS decomposition in this case, and based on that, we were able to derive the analytic formula for the active sterile mixing as the function of this third non-unit singular value. Based on that, we performed the numerical analysis, and we have obtained upper bounds, which in some cases are much better than the previously known in the literature. Moreover, in many cases, we were able to get the non-zero lower bands for this active sterile mixing, in this case with one additional neutrino. Let me now briefly discuss this potential of the Z boson decay in the study of sterile neutrinos. We will focus today only on this tree diagram because the loop diagrams depend strongly on the particular models, and we are mostly interested in this intermediate and light sterile neutrinos because then coupling between light and sterile neutrino is not that great, so the signals should be visible in future colliders. So our motivation for the study was the recent update for the effective number of active neutrinos, and we wanted to see how this translates into the estimation of active sterile mixing. To do so, we check this in the simplest 3+1 model, which we must, and this must be emphasized that this is only a toy model because here two neutrinos are massless, which contradicts the current status. However, here you can see the setup, and the sign alpha, which corresponds to the active sterile mixing, is given as is proportional to the masses of these two massive neutrinos. And for this simple model, the effective number of active neutrino can be parameterized by the X and Y parameters, which are given as the ratio of masses, and is given by this formula. If we plot it, we will get the following figure. And if we look at the straight line y equal x tangent square alpha in such a way that it must lie below the experimental given limits, we will be able to extract the sine alpha and in that way to estimate the active sterile mixing. So the result of this procedure are given below, and you can see that the improvement in the recent improvement in the estimation calculation of the number of active neutrinos give the significant improvement in the estimation of active sterile mixing. So this brings me to my summary. So in our analysis, we studied the entire neutrino mixing matrix. We used the unitary dilation procedure to study separated scenarios with 1, 2, and so on neutrinos number. So far, we derived the analytic formula for the scenario with one additional neutrinos. On top of that, we performed the numerical analysis and obtained upper and lower bands for the active sterile mixing. Now we are working on the derivation of analytic formula for the scenario with 2 and 3 additional neutrinos, and then we will make the numerical calculation to predict active sterile mixing. And finally, encouraged by this toy model, and we want to pursue further the study of the Z boson decay in the estimation of active sterile mixing. By now, we want to focus on the physical model and also take into account the loop correction. Thank you very much.
Thank you for clear and concise talk. We can have one quick question. I see no questions. In that case, let me move on. Thank you very much.
Thank you.
The last talk in this session is a standard model explanation for the mini-BOONE anomaly by Ara Ioannisian.
Hi, do you see my slides?
Yes.
Thank you. I will talk about mini-BOONE anomaly, that this electron-like events excess, that I am Ara Ioannisian from Yerevan Physics Institute, Armenia. So mini-BOONE anomaly is looked to the nu E oscillation in short baseline, and they found excess of electron-like events about almost 5 sigma. Is how to look to that. It's from 4.5 to 5 sigma, and excess is mainly in the 500 MeV region. So it's delta resonance region. So it's well known that mini-BOON cannot separate electrons or positrons from photons. So this is a problem. And then if you have more photons, you can easily explain mini-BOON, this anomaly within the standard models. So number of photons from neutral currents is estimated in mini-BOON from number of registered pi zeros, and that's the problem. And I will look to the this problem from existing experiments, from A2 experiment in the mines. So it is accelerator with real photons from 40 to 1.6 GeV. So these real photons, they bombarded different nuclei from carbon, oxygen, I don't know, to plumbum, and then look to the pi zero production. And then this pi zero, I will assume, I think very realistic assumption that this pi zero escape factor, which I will calculate or extract from A2 experiment. This is the same for Z boson production, so neutral currents. So in other words, this escape factor from nuclei is unaffected by its production channels. So if you produce via photons or Z boson, so you produce delta or something like that, and then it has this separate life, and so the escape factor for pi zero will be exactly the same. I will assume it's exactly the same. So this I will show that this will significantly lower the number of unexpected electron-like events even in mini-BOON, and I will give also prediction for short baseline neutrino program at FNAL, and prediction of bound nuclear decay. So it's a proton, or in other words, proton decay from liquid scintillator or water Cherenkov or liquid argon detectors. Sorry. So this is a mini-BOON experiment. So it's about 500 meter.
I'm sorry. I'm afraid you are switching slide, but we cannot see your slide. We are still seeing page 1.
Okay, too fast. So you cannot see my slides?
We are still looking at page 1.
Oh, okay. That's in maybe connection problem. So anyhow, this I will put necessary just a slide. Did you see this 2006 this mini-BOON update page now? Page 595?
Not yet.
Yes?
No. Could you try stop sharing and restart sharing?
Okay.
And now it changes. Page 6 is shown.
Page 6 is shown. I'll go to page 5. And page 5 is, do you see now page 5?
Yes.
Okay, page 5. This mini-BOON update paper from last month. So the point is just these experimental points, and this color areas is just backgrounds. So I will bring your attention to yellow, this delta to photon resonances. I will try to convince you that this array is much wider, and if it's wider, then effect of this new unexpected events will be lower. So again, this is from mini-BOON paper from last month. You will see this in the red, neutral current delta goes together. They estimate to have about 250 events, and total excess events is about 560. So if you increase these numbers, you will decrease these excess numbers, and now it's about 4.7 sigma or about 5 sigma, and then it will go to, I will show that you go to up to 3 sigma. because I will show you. Okay, and MiniBooNE, as I said, MiniBooNE estimate the number of photons due to neutron currents and interactions from registered number of pi zeros. If you have just for free nucleons, we assume that it's all nucleons in the carbon, for instance, is free. In that case, you will have about 1% of photons per pi zero production, is not 0.9%. And then if we assume that everything is free and there is no problem of going out of creating pi zeros and so on, and no other no higher resonances, non-resonance contribution, not coherent effect. Just in this case, it is 0.9%. And then, okay, I will assume that this page is from page 17 from paper from MiniBooNE last month. So on page 17, you will read that delta to n gamma background is determined from the delta current piezo events. And then if you look to the very carefully, they include all kind of production in pi zeros. It is a coherent scattering, higher mass scattering, and incoherent scattering is 52%. And then, but in photon production, they consider only from delta resonance, and they found also the escape factor from nucleus. They assume 62.5%, which is very, very high. If you look to the, for instance, in proton decay, any from carbon or oxygen, you will find easily it's about, people calculate it's about 40%. It's not 62.5%, which is too high. And for these numbers, they got this ratio of number of photons per registered number of pi zeros is 0.9%. And then I will show you that P0 escape factor from nucleus. I will go step by step and explain you that P0 escape factor from nucleus is different than people assumed in MiniBooNE. And there is also non-zero resonance contribution additional to delta resonance. Also, there is a coherent photon production from carbon, and also there is a high resonance contribution which is extremely small, and I will not focus on them. So then I will go to A2 experiment again from MINDS. It's a MAMI accelerator. So so it's very nice, very precise experiment, and they would put this bombarded this from different nuclei, from carbon, calcium, niobium, plumbum, proton, deuterium. So you will see if you normalize by A effective is just A number of nucleons in the nuclei to the 2/3, they all match each other in the region which is very interesting for us, is the pi zero production cross section. Pi zero production cross section. So it means that pi zero has difficulties to go out from the nucleus when you create them, and the suppression factor is exactly A to 1/3. A 1/3. If you so without final state interactions and with final state interactions, if you calculate everything, it goes to A 1/3. A 1/3 for carbon is just for 12 is just about 43%. So instead of 62.5%. So only for delta resonance, if you add this escape factor by simple mathematics, you will see that it goes to about 25% more photons than MiniBooNE assumed in recent calculations in the MiniBooNE paper last month. So again, I will underline that as well known, the pi-nucleus interaction cross-section is proportional to the surface area of the nucleus. By constant, the total proton absorption cross-section on the nucleus is proportional to its volume and scales as A. Meanwhile, the photons created in delta decays will leave the nucleus, and that cross-section will be proportional to the atomic number of the nucleus, A, volume of the nucleus. Thus, we conclude that the ratio of photon to pi zero production via delta resonance in nuclei is proportional to A to 1/3. And then I will go to the non-resonant contribution to this process for photon production. And you will see if you go to Cyril de Jong paper, it goes to more than 40%, but it's 40%. So it's 40% above the delta resonance. So this delta plus N is about 40% more. But they have problem with so-called contact terms. Also, they mentioned that this contact terms is contribute mainly in large and high energy region. They said about more than 1 GeV, but I will put lower. And then I assume, also based on the other publication by Spanish group, that increase in the non-resonant contribution is about 10%. So the Spanish group, I mean this group, Wang, Alvarez Ruzo, Nieves, Juan, and so on. So if you look to this paper, this last paper, there are several papers. They have several papers. So for new mode and electron energy range is of 300 MeV for 475 MeV. Is the GeV must be here. Is wrong. So then you will see that this factor R. This is the delta resonance, the non-resonance coherent, and this higher resonance contributions. It will be this the delta is 1, 10% for non-resonance, and about 30% for coherent contribution, and very small from higher resonance. So if you multiply everything, you will get about 60% more photons. So electron-like event excess at MicroBooNE is they said in the table is 560. So which is error 119, which is 4.7 sigma. So if you put 1.6 times more photons, so if you put 1.4, they assume that they have 250 photons. So if you put 60% more, you will get about 409 only 409 unexplained events. If 409 unexplained events is only 3.4 sigma instead of 4.6 sigma. So only looking to these things. So the escape factor and also non-resonance and coherent contribution. Against the public last month's paper by MicroBooNE, instead of 4.7% sigma more events, you will have only 3.4 sigma more events. Again, I explained this. I put here 1.8 my recent papers, but I put much more. You will see these numbers of MicroBooNE, and this is with 1.8, you will see that almost they reached the points, and there is no problem with okay, this last one is much higher, and then of course you will see you will go not to only 3.4 sigma, and this anti-neutrino cases. So then it is the same for this neutrino oscillation formulas and so on. But I want to underline once more that this factor, escape factor, was calculated that in 2008 by by this paper. Again, if you look carefully, that almost the same people, which is calculated recently in 2015. So the similar value 2.4 for pi-zero array suppression factor was briefly reported in the section 3.3 without strong statement conclusion in that section and in the paper, in the full paper. So outbound pi-zero momentum. So all pi, it's unclear which pi-zero they include, or with pi-zero with momentum 200 MV. That's another question to these people, to that publication. But anyhow, they found almost the same suppression factor as I found from analyzing A2 experiment data. Again, I want to just I will go to further. So liquid, so short baseline neutrino program at Fermilab, they want to check the LMB. One of the goals of this program also to check the MicroBooNE results. So, but I want to say that in the software, they have to change pi-zero escape factor from, I don't know, 60.62% to 30% because argon is much bigger nucleus, and escaping P0 is much difficult than from carbon. So it is 30%. Again, from proton decay, so if you go to from oxygen, it is about, as I said, 40%. So it is more close to which people assume it to have. And for argon, escaping factor will be about 30%. So if we do have proton decays, positron will go out easily, but each only third by zero you will observe. So in conclusion, the reduced neutral pion production rate plus non-resonant and coherent proton production will yield at about 60% more photons as previously expected, thus significantly lowering the number of unexplained electron-like events at mini-BOONE. For SM short baseline neutrino program at Fermilab, it must be taken into account that in their software that they, because I heard that they're using, maybe I'm wrong, they're using a mini-BOONE software for argon also, so they have to change this escape factor for pi zeros, and it will be 30% again. Thank you.
Thank you very much. I'm very sorry, we are already invading the next session. So thank all the speakers in this session. So Thomas, could you take over?
Thomas, ask question. Thomas asking, okay.
One question, yes, of course.
Okay.
I see no question. Okay, thank you very much. So Thomas, please continue. I'm very sorry.
Okay, so yes, hello everyone. We continue directly with the next session, and let us start. First speaker, Jason Leung, about testing MSW effect in supernova explosion with neutrino event rates.
Yes, and first, can you hear my voice?
Yes.
Oh yeah, great. Then let me share my screen. Wait a moment.
Okay, maybe you can try now to share.
Yeah, sure. Wait a moment. Okay, can you see my slides?
Yes.
Now I enter into full mode, and can you see clearly on page 1, page 2, and page 3?
Looks good, yes.
Very nice. Then I'm going to start
start.
now. Okay. Today I'm going to introduce a method to test whether the MSW effect happens in a supernova or not. And before we define something new, let's have a review of some useful neutrino oscillation formulas. If the MSW effect does not happen in a supernova, then probably the final neutrino fluence or fluxes on Earth is governed by the vacuum oscillation formulas. And on the other hand, if this happens, then the final fluxes on Earth should be given by the below two sets of formulas, which is invented by 3 people called McKeith, Smirnov, and Wolfenstein. And with all these formulas in hand, we are now able to calculate any neutrino event number on Earth. And together with a given simulation, supernova neutrino simulation data. For example, this one is a supernova neutrino simulation done by Gachin's group and Fisher-Cecile. And from a glance at these 2 plots, one can immediately see that actually they have a common time evolution pattern. A sharp peak emerges in the profile of the electron neutrino primary emission during the neutronization burst, which is a black curve here. There's a sharp peak here. And together with the formulas I have just mentioned in the previous page, note that a huge amount of electron neutrino is switched to other flavors according to the MSW oscillation formulas. As here, as you can see here, for electron neutrino, the final electron neutrino fluence on Earth actually comes from mu and tau primary neutrinos. And in inverted hierarchy MSW effect, it is come from partially the primary electron neutrinos and partially from the mu and tau neutrino correspondingly. Therefore, one can deduce that any experiment which is sensitive in looking for electron neutrinos will be helpful in determining the oscillation effect in a supernova. For example, this one is the argon neutrino absorption rate, which can be measured in a DUNE experiment. And we calculate the corresponding event rate by using these two groups simulations. And you can see that the huge amount of electron neutrinos, which are the flavor in the MS oscillation. Therefore, the red curve and the blue curve is highly suppressed, and we can't even see a peak in the MSW NH scenario. And a sharp peak is still retained in the vacuum oscillation and the inverted hierarchy cases, but not for normal hierarchy. Therefore, the argon neutrino absorption rate actually has the potential to discriminate the oscillation effect. And here is an idea called, or an object called cumulative distribution, which I read the paper. This idea actually comes from a paper written by Sir Pico et al. They use this cumulative distribution and to calculate how fast the event number accumulates. And later on, they performed a quantitative analysis by measuring the distance among different curves, among different models. And here, we tend to construct a preliminary analysis by just simple inspection on the time evolution patterns instead of such kind of complicated analysis. Therefore, we defined this object called the cumulative event ratio. And in today's talk, I'm going to introduce two kinds of cumulative event ratio. And here is the first one. The definition is here. We pick the cumulative distribution as a numerator here and compare with a diagonal straight line. Why a diagonal straight line here is because actually this line penetrates through the left bottom corner and right upper corner. It's exactly the same characteristic of a cumulative distribution. We start from 0 and cumulative to finally to reach to a number 1. With this definition, we are able to create some function. We start and end with the same value. And finally, we can observe which pattern it is in. It may be concave curve, convex curve, or just a straight line. And the result applied to Gachin's group and features as well applied to their simulation, then we get these curves. One can immediately realize that actually for the MSW neutrino hierarchy case, the curve always looks convex. And the rest of the two looks concave, but we can still put a criteria or put a line to separate them. And here you can see that for the black curve is indicating the vacuum oscillation. The maximum of this black curve always greater than or around 0.5. Therefore, this may be a criteria to separate the vacuum oscillation and the MSW oscillation, even if we do not have any simulation models to compare with. It means that once we obtained a supernova data, and then we can calculate this cumulative event ratio and see whether the maximum of that curve greater than or smaller than 0.5. If it's smaller than 0.5, then we can immediately say that actually MSW effect just happens in a supernova or vice versa. But here we only focus on two simulations data, and later on here we apply this method in another simulation done by Burroughs et al. And Nakazato et al. On the left panel, actually we can see that this method is applicable in their simulations. The greatest number of the black curve is around 0.5. Therefore, I think it's still okay to use our criteria, but not for Nakazato et al. Not for the model, not for the simulation done by Nakazato et al. The reason here, I guess, is because in their simulation, the sharp peak is not that clear and not that sharp in the beginning of the supernova. And anyway, we have done we have applied our criteria in 4 simulation series, and 3 of them success, then I think it's okay. And here I want to show another version of cumulative event ratio, which is the definition is here. We use the blue curve here instead of the straight line I have defined it before to replace the diagonal lines. Then we can see that, or we can immediately imagine that the result should be either concave curve, convex curve, or even a straight line. The idea here, we choose the blue curve divide by itself, as you can predict that it should be a straight line. Therefore, one can immediately separate different oscillation scenario in this figure. The result like this, we have a concave curve for the vacuum oscillation, a horizontal straight line for MSW inverse hierarchy, and a convex curve for MSW normal mass ordering. But this is just an ideal case because we choose the simulation SMS experimental data. Therefore, the numerator for inverted hierarchy here actually is the same as the denominator. But this is just something like a toy model. Is a check. Is to demonstrate our idea. Therefore, it is quite impractical. But practically, we can use other simulation as the simulation pool, which puts in the denominator here. And here is the result. The idea is like this. We treat the Gachin and Fisher supernova neutrino simulations as an experimental data. And we use Burroughs supernova neutrino simulations for our simulation pool, which for a comparison with the experimental data, then we can get these 2 plots. And as you can see here, if we are in vacuum oscillation, it means that if the MSW effect does not happen at all, then the region here above 0.4, there should be a region greater than 0.4 appears in the curve we obtain later on. But if we do not see that curve, or we cannot find any number greater than 0.4, then probably the MSW effect happens in a supernova. And the criteria in detail is like this. There's a region in cumulative event ratio for vacuum oscillation is greater than or around 0.4. And if it is a inverse hierarchy in MSW oscillation, then the value should in between 0.3 and 0.4. And the rest is a convex curve for the MSW effect normal hierarchy. And please note that here is that all these criteria are based on or relies on the sharp peak in the electron neutrino primary emission during the neutronization burst. And therefore, this kind of method maybe cannot apply in Nakazato's simulation, but at least this method works in Gachin's simulation, Fisher's simulations, and Burroughs simulation. So here we come to our conclusion. In the beginning, we proposed a simple method to verify the MSW neutrino oscillation effect in supernova. And then the argon neutrino absorption rate has a huge potential to distinguish between the vacuum oscillation and the MSW neutrino oscillation. Later on, based on this argon event rate, we construct 2 versions of cumulative event ratios. And one of them is we put an ad hoc quantity called a diagonal straight line. And another one is based on some simulation data. We need a simulation pool in the denominator. And both of them actually the evolution patterns of both both event cumulative ratios can be effective in determining whether the MSW effect occurs in supernova neutrino propagation or not. Yeah, and this will be all I would like to say for today. And here is a reference I've used in this research. Thank you so much.
Okay, thank you for the talk. We have time for a quick question. Please raise your hand if you want to ask a question. Okay, I don't see any question.
Okay.
Good. So thank you again, and
yeah, thank you
let
very
us
much.
move to the next talk.
Okay.
The next talk is by Rafal Maciula about production of tau neutrinos and fixed target experiment SHIP.
Okay, can you hear me?
Yes.
Okay, so let me share my screen. Do you see my slides?
Yes, looks very good.
Okay, so good morning to everyone. Today I'll be talking about production of tau neutrinos and tau antineutrinos in a fixed target experiment SHIP. This work was done in collaboration with Antoni Szturek and Iza Babiarz and Jakub Zaremba in the Institute of Nuclear Physics in Krakow. Results of this study are collected in the article, which has been published very recently in JHEP. And here is the outline of my talk. After a brief introduction, I will discuss two different mechanisms of DS meson production via leading fragmentation of charm quarks and via subleading fragmentation of strange quarks. Then I will describe production mechanism for tau neutrinos, and finally I will present our predictions for differential cross-sections, neutrino cross-section, as well as for number of observed tau neutrinos at SHIP experiment. Okay, so motivation behind the study comes directly from the physics of tau neutrino, which is still after 20 years from the discovery, the less known particle of the Standard Model. Since its discovery in 2000 by the Donut experiment, with the observation of 9 candidate events, only after 10 events of tau neutrinos have been detected so far by the OPERA experiment during the search of muon and tau neutrino oscillations. Recently, for the first time, the 2 candidates for astrophysical tau neutrino were classified by the ICHEP observatory. To improve the situation in the tau neutrino sector, we need really neutrino factories, which will be able to produce much more tau neutrino and antineutrino events, and to study their properties and cross sections, as well as to perform first observation of tau antineutrino. One of such a dedicated experimental projects now in the comprehensive design phase at the CERN SPS is the search for hidden particles, SHIP experiment. So SHIP is a general purpose fixed target facility at the CERN SPS accelerator designed to explore the domain of hidden particles as well as to make measurements with tau neutrinos. For the latter purpose, SHIP is planned to be a source of copiously produced tau neutrinos and antineutrinos, which will come from the direct and chain decay modes of DS meson. The experiment will be driven by 400 GeV proton beam, chosen to enhance charm cross section as much as possible. The beam will be dumped on a molybdenum target, which has a short integration length, which is chosen to maximize neutrinos from charm hadrons. While minimizing those coming from kaon and pion decays. Neutrinos produced at the beam dump will be able to be observed in the neutrino detector with LED. So the configuration and the geometry of the SHIP detector will allow to collect particles in the very forward direction. So as a starting point for this analysis, we need to calculate differential cross-section for DS meson production in proton molybdenum interactions at 27.4 GeV. This can be done basing on elementary proton-proton and proton-neutron cross-sections, neglecting nuclear effects, which are expected to be rather small, if not negligible, and which should not affect the numerical predictions under interest here in this study. As I already mentioned, we consider two different mechanisms for DS meson production, leading C to DS fragmentation, where we need CC bar per production cross-section and a model for heavy to heavy hadronization, as well as subleading S to DS fragmentation, where S and S bar quark production cross-section and also light to heavy hadronization model are needed. Charm quark production in QCD at high energies is dominated by gluon-gluon fusion. However, at lower energies relevant for SHIP, also quark-induced processes are important. Here we include both types of the partonic processes. The CC bar per production cross-sections are calculated in the collinear next to leading order approximation using Phong framework, as well as in the KT factorization approach with transverse momentum dependent parton distributions. Okay, so the transition from charm quarks to DS meson is done with the independent parton fragmentation picture using Peterson fragmentation function with epsilon parameter fitted to E plus E minus data, and by normalizing the meson cross-section by known with some uncertainty known fragmentation probability, which is extracted at the level of 5 to 9% from different data sets. The independent parton fragmentation works very well for the LHC energies and leads to a good description of the LHCb and the Alice open charm data. There is a lack of low energy open charm data. However, from theoretical analysis of existing measurements of total charm cross sections for charge D meson in fixed target experiments, we conclude that low energy charm data seems to be slightly underestimated by the standard calculations, and there is a room for some missing strength. Okay, so the S and S bar quark production cross sections are calculated here in the leading order collinear factorization with onshore initial state patterns and with a special treatment of mini special treatment of mini jets at low transverse momenta, as is adopted in PETIA by multiplying standard cross section by somewhat arbitrary suppression factor. In the numerical calculations, we use three different collinear parton distribution functions, which contains an asymmetric strange C quarks and anti-quarks. And comparing charm and strange quark differential distributions, we get a similar cross sections in both cases. And what is interesting for us, the strange quark production may dominate over charm at very forward rapidities. Okay, so in contrast to the charm quark fragmentation, the fragmentation function for S to DS transition is completely unknown, which makes the situation more difficult. For the case of light to light transition, rather soft fragmentation functions, which are picked at small z values, soft fragmentation functions are supported by phenomenological studies, and on the other hand, in the case of, for example, BC meson, the fragmentation function for B quarks was found to be peaked at large Z, while a fragmentation function for C quarks is shifted to intermediate Z values. So in principle, one could expect a similar behavior of the C to ds and S to ds fragmentation functions. Okay, so besides the shape of the S to ds fragmentation function, the relevant fragmentation fraction is also unknown. It needs to be extracted from experimental data. First attempt was done very recently by us when discussing D plus S and D minus S production asymmetry, which can be explained by the idea of subleading S to ds fragmentation. So from this study of the asymmetry, we roughly extracted the S to ds transition probability at the level of 3%. However, it requires further studies. So now let me show predictions for the energy distribution of DS mesons in the laboratory frame for proton molybdenum scattering at ICHEP. Here we show separately the leading and the two sub-leading contributions, as well as their sum. The left and the right panels correspond to the NMHT and NNPDF PDFs. Pretty much different results are obtained for the two different PDF sets, especially for large meson energies. So depending on the collinear PDFs used, our model leads to a rather small or a fairly significant, sorry. Oh. Let me go back. I don't know why. Sorry for that. Okay, so let me go. Let me repeat that depending on the collinear PDF used in our model, we get a rather small or a fairly significant contribution to the DS meson production at large energies, which comes from the S or S bar quark fragmentation. So a future measurement of DS meson at low energies would definitely help to better understand underlying mechanisms and reduce the uncertainties. So having predictions for DS meson production, we can start analysis of tau neutrino production for this purpose, two different DS meson decay modes, the direct and the chain, has to be included in the model calculations. The direct decay channels of DS meson are analogies of the standard test. Oh, sorry. Okay. The direct decay channel are the analogies of the standard textbook cases of pion decays discussed in detail in the past. The same formalism used for the pion decays applies also to the DS meson decays. Since DS meson has spin 0, it decays isotropically in its rest frame. However, the produced tau leptons are polarized in its direction of motion, which is due to the structure of weak interaction in the standard model. The tau lepton takes almost whole energy of the DS meson. Of course, to calculate cross-section for neutrino production, the relevant branching fraction must be included with, which is rather well known, and the value is about 5%. The value is about 5%. Okay, so the subsequent tau lepton decays within the chain mode are rather complicated due to having many possible decay channels. Nevertheless, all confirmed decays lead to production of tau neutrinos. The purely leptonic channels cover only about 35% of all tau lepton decays, and the remaining 65% are semi-leptonic decays. So both direct and chain decay modes lead to symmetric production of neutrino and antineutrino. The neutrino-antineutrino asymmetry might appear only as a result of the as plus ds minus asymmetry. So the energy-dependent flux of neutrinos can be written as follows. I will not go through the detail, but I would just say that this formula can be used to estimate number of neutrinos or antineutrinos produced at the beam dump. For the decays of ds meson produced from charm quarks fragmentation, we obtain 1.32 times 10 to 15, which is a huge number. However, only a part of the neutrinos produced at the beam dump will be then observed in the detector.
You have about 1 minute left.
Okay, I will accelerate. So how many neutrinos will be observed in the SHIP experiment depends on the cross-section for neutrino scattering of nuclei of the target. In the case of the SHIP experiment, a dedicated LED target was proposed. So the number of neutrinos observed in the LED target depends on the cross-section for neutrino LED and antineutrino LED interactions, which can be obtained from elementary cross-sections. The elementary and nuclear cross-sections strongly depend on neutrino energy and are dominated by charge current deep inelastic scattering. So the cross-sections in our study are calculated using the Nuvro Monte Carlo generator. So now I'm going quickly to the final results. Here I show predictions for the laboratory frame energy distribution of tau neutrinos, including SHIP detector cuts. We show separately leading and subleading fragmentation contributions. And again, we obtain two different scenarios for the two different PDFs. The MMHT set leads to a negligible subleading contribution in the whole energy range, while the NNPDF set provides the subleading contribution to be dominant at larger energies. If such distribution could be measured by the SHIP experiment, then they could be used to constrain the PDFs in the purely known kinematical region. However, it will be extremely difficult. So the energy distributions shown on the previous slides are a bit theoretical.
Sorry, can you conclude soon? We are already in overtime. So please conclude.
Okay, so let me just summarize the final results. So here I show a number of neutrinos observed in the target per interval of the neutrino laboratory energy. So after integrating the above integrands, one gets numbers of neutrinos collected in the table on the last slide. So quite different numbers are obtained for different considered scenarios. However, the main message as my conclusion is that we predict from 800 to 2000 neutrino events at SHIP coming from charm quark fragmentation, and about extra 200 to 400 events coming from possible strange quark fragmentation. So I think now I can stop at this moment. Thank you very much for your attention.
Okay, thank you for the talk. I think we have no time for questions. We need to move on, but please use the MetaMost channel where you can pose questions and have discussion with the speakers. So let's move to the next talk. Next talk is by Yadi Datta about matter versus vacuum oscillations in atmospheric neutrinos.
Hello, can you hear me?
Yes.
Okay, so I should share my screen, okay?
Yes.
Can you see my screen?
Okay, looks good. Very good. Please start.
Okay. Hello, good morning, everyone. I am Jaideep Datta. I will like to thank the organizers for giving me this opportunity to present my work in this conference. I also like to thank the INO collaboration for their help throughout our work. So I will be talking about matter versus vacuum oscillation in atmospheric neutrinos. So neutrino oscillations driven by the larger mass square difference delta 3(1) has been observed in different neutrino experiments like atmospheric neutrino experiments, Super Kamiokande, and long baseline accelerator experiments like MINOS, T2K, and NOVA. The main oscillation signature in all these experiments are basically nu mu and nu mu bar disappearance data. So this deficit in all these experiments was analyzed initially under the hypothesis of vacuum oscillations. In the case of long baseline accelerator experiments, the survival probability of nu mu and nu mu bar essentially are the same for vacuum and for matter modified oscillations. So the magnitude of delta 31 and the value of sine 2 theta 23 obtained from these experiments will be very close for both the hypotheses. For long baseline accelerator experiments, nu E and nu E bar appearance data is sensitive to matter effects, but they are also sensitive to the unknown CP violating phase delta CP. So a recent work by S. Bharti et al., they have shown that the present long baseline accelerator neutrino experiments cannot make a distinction between vacuum and matter modified oscillations. Matter effects are already established in oscillations driven by the smaller mass square difference delta 21. So given the matter effect and delta CP degeneracy, the determined value of delta CP depends on the oscillation hypothesis to fit the data. So therefore, it is imperative to establish the signal of matter effects independently before measuring the delta CP. In the case of atmospheric neutrino, the nu mu and nu mu bar survival probabilities are expected to undergo significant changes due to matter effects. However, at present, Super Kamiokande is able to make only a small distinction between them. The charge identification capability of ICAL at INO gives it a good ability to distinguish between vacuum oscillations and matter modified ones. So in this slide, I'm going to just give a idea from where we are. The INO will get the signal for this matter versus vacuum oscillation. So when these electron neutrinos are traversing the earth matter, they undergo interactions with the electrons present in molecules, and that's why they get a matter potential, and that actually modifies the oscillation probabilities. So the matter modified oscillation probability for this work has been calculated numerically using a Newcraft code. So in the adjacent plots, I have shown the survival probability of nu mu and nu mu bar in the energy range 0 to 20 GeV for a path length of 5,000 kilometers. On the left panel, you can see the oscillation probabilities, the survival probabilities of nu mu are plotted for normal hierarchy and inverted hierarchy for both matter and vacuum hypothesis. So you can see in this in the left panel that when it is considered that when it is considered when we look at nu mu survival probability, if we have the survival probability actually differs a lot when normal hierarchy is assumed, but in case of inverted hierarchy, the difference is not significant. But that is opposite in case of nu mu bar survival probability. In this case, you see that the survival probability differs significantly if we assume inverted hierarchy. So matter and vacuum oscillation discrimination will come from nu mu disappearance data for normal hierarchy and nu mu bar disappearance data for inverted hierarchy. So for our work, we have used nuance event generator to simulate 500 years of unoscillated atmospheric neutrino events in the detector using Kamioka flux. So nuance provides the particle ID and momenta of all interacting particles. So this information has been passed to giant force simulator of ICAL, which actually mimics the detector response. The reconstruction code from the heats in the detector form tracks of the muons and reconstructs their momenta, directions, and charge. These reconstructed and direction of tracks have been used to bin the events. Oscillated nu E and nu E bar events will contribute to nu mu and nu mu bar events. To take this contribution into account, we took all nu E and nu E bar events and redefined the leptons, electrons and positrons and muon as muon and antimuon respectively. These redefined new muon and antimuon events are reconstructed using the ICHEP code. So the parameter values shown in the adjacent table have been used to calculate the matter modified oscillation, varying the sine square theta 1, 2 and delta 2, 1 in the 3 sigma range has negligible effect on the probabilities for atmospheric neutrinos. So they were kept fixed for vacuum oscillation calculation. When sine square theta 1, 3 and delta 3, 1 are varied in their 2 sigma ranges, chi square minimum came at the best fit value. So the marginalization was not done for them. Sine square theta 2, 3 has been varied over a range from 0.4 to 0.64, and matter and vacuum oscillation for our experiment is insensitive to delta CP. So to beam our events, we have used 17 track momentum beams and 90 track direction beams. Oscillation signature is only visible for upgoing events, so only positive values of cos theta track is considered. For horizontal events, track construction is not possible in our detector. So we have considered cos theta track in the range 0.1 to 1. As track direction reconstruction is very accurate for ICHEP, the cos theta track beam is taken to be 0.01. To calculate the chi-square, we have made data samples and vacuum oscillation samples. So the matter oscillated events are used as data and two sets are formed, NIJ data mu minus and NIJ data mu plus. So this I stands for the track momentum and J stands for the track direction. Vacuum oscillation as a hypothesis was tested against the data and to get the vacuum data set, we have we make two other samples. Those are NIJ vacuum mu minus and NIJ vacuum mu plus. We calculate the test event samples using the following equations, where we have used three systematic errors pi ij k and each with its pool parameter xi k. The first systematic error is dependent on flux normalization, which is independent of track momentum and track direction. The second one is the systematic error dependent on track momentum, and the third one is dependent on track direction. So we take the flux, the systematic error dependent on flux normalization to be 20%, and we have taken it as independent of track momentum and track direction. We constructed a transfer matrix to convert event spectrum in neutrino energy to event spectrum in track momentum. Using this transfer matrix, we have calculated the second systematic error, pi ij track momentum to pi I track momentum, and using the tilt error in atmospheric neutrino calculation. Similar procedure is used to calculate the third systematic error from the direction dependent systematic error of atmospheric neutrino. We use the Poissonian definition of chi-square and also added the prior JK square for the pool parameters. The 500 years data and test event samples were divided by 50 to get the event samples for 10-year exposure time. Marginalization over sine square theta 1 3, delta 3 1, sine square theta 1 2 and delta 2 1 has no effect on chi-square minimization. Marginalization for sine square theta 2 3 has been done in the range 0.4 to 0.64 in steps of 0.02. JK has been varied. The pool parameters has been varied in steps of 0.1 between -3 to 3. Marginalization over delta CP has been carried out using 4 test values, 0 degree, 90 degree, 180 degree and 270 degree. This has negligible effect on chi-square minimum. Present global best fit value for delta CP is close to 270 degree. We repeated our calculation with these as the input value for matter oscillations. The results remain unchanged. So in this slide, I am showing the result of our work. So in the adjacent figure, you can see that ICAL is capable of distinguishing between vacuum and matter modified oscillations with chi-square 11.8 for normal hierarchy and 9.5 for inverted hierarchy for 10 years of exposure time. In those plots, you can see there is a dashed line which actually shows the ICAL sensitivity when we have not taken the capability of ICAL charge identification of the leptons. So in that case, you can see the chi-square reduces to half. So in a recent superconductor work, they have looked for non-standard matter effect. They parameterized the matter term as alpha into standard matter term and varied alpha in the range 0 to 2. The vacuum oscillation corresponds to case of alpha equals to 0 and the standard matter oscillation corresponds to alpha equals to 1. The same was carried out for our work also. In the adjacent plot, you can see that we can distinguish the matter and the vacuum oscillation very clearly, even for the wrong sign also. So I would like to conclude my work with these two statements that ICAL at INO is capable of establishing the Earth matter effect in atmospheric neutrinos with chi-square 11.8 for normal hierarchy and 9.5 for inverted hierarchy for 10 years of exposure time, irrespective of the unknown CPU violating phase. The sensitivity reduces to half once the charge identification capability of ICAL is neglected. Thank you.
Thank you very much for the talk. We have time for question, please. Is there any question here? No? You can raise your hand and ask a question. Okay, there seems to be no questions, so thank you again, and let us move to the next talk. The next talk will be on studies of quantum mechanical coherence effects in neutrino nucleus elastic scattering by Vivek Sharma.
Yeah, so I'm sharing my screen.
Yes, we can see
so,
your screen.
Can you see?
Yes, very good.
Okay,
Please
so thanks to organizers to giving me a chance to present this work. And I'm going to present about the quantum mechanical coherence effects in neutrino nucleus elastic scattering. So this is the outline of my talk. So neutrino nucleus scattering is well defined in standard model, and its cross section is given over here. And here you can see that cross section have a term of epsilon z minus n square. So because of small Weinberg mixing angle, this epsilon is very small, and hence this term gets negligible in comparison to n, and one can say that this cross section is proportional to n square, so which can be seen over here. So this is the total cross section versus incident neutrino energy, and you can see as the mass of the target increases, the cross section also increases. So to see this scattering, to observe it, the requirements are high neutrino flux, and because of the nuclear recoil of very low energy, one should have low threshold detector with better resolution and quenching factor if needed, and understanding of ambient backgrounds and shielding from other gammas, neutron backgrounds, etc. And if the source can be turned off and on, then it's also good, like for the reactors and stopped pion neutrinos. So why this scattering is important? It has an important role in supernova explosion, and it is also a test for standard model weak electroweak interaction. And beyond standard model physics can be probed with the help of neutrino nucleus scattering if there is some deviation from the standard model cross section. And it is a probe of quantum mechanical coherence effect in electroweak process. Other than this, it can be used for reactor monitoring as a portable device. It can be used, and also it has importance in the dark matter searches, as neutrino nucleus scattering gives a irreducible background, which can be seen over here in the right side plot. So I'm working in Texono collaboration, and this experiment is located at Kaohsiung Neutrino Laboratory, which is shown over here in Taiwan. And the theme of the experiment is low energy neutrino physics and dark matter searches. We have collaboration with India, China, and Turkey. And this is the diagram of schematic diagram of reactor building, and here is the reactor core, and at a meter of 28, at a distance of 28 meters, there is a laboratory in which the detector is situated, so which is shown over here. So there are plastic scintillator at 5 site, which can be seen here, and inside is the shielding, which is shown here, which have different layers of lead, stainless steel, boron-loaded polythenes, and copper. So there is a vicinity over here in between, in which we used to place our detectors. So we have also worked on CSI detectors, but from a long time, we are now working with point contact germanium detector. So this is the expected neutrino flux at this site. And right now we are using cryocooler germanium detectors, so which is covered. It's with a sodium iodide detector and other shieldings. So we are working with both P-type and N-type point contact germanium detectors. So these are the old picture, and this is the new version of the detector, which is electro-cooled. So this liquid nitrogen dewar is changed with this one. So here we categorize our detectors into 4 generations. So germanium generation 1 and 2 are liquid nitrogen based detector, which have maximum mass up to 900 gram, and they have best threshold up to 300 eV, while third and 3+ generation are electro-cooled detector, and we have achieved with 500 gram mass the threshold of 200 eV with 70 eV full with half max. And soon in near future we will get generation 3+ detector, which maybe get more better full with half max resolution and threshold. So the advantage of G3+ detectors are they have controlled microphonic noise, and the temperature of crystal is also customized. You can change it as per your need, and there is improved point contact electronics, and of course no liquid nitrogen is needed. So for reactor neutrinos, we have been studying these different processes, and which are already, in which 3 of them are already being published. And right now we are focused on neutrino nucleus coherent scattering. So the expectation at Kaohsiung Neutrino Laboratory is can be seen in this slide. So here is the incident neutrino energy versus the maximum nuclear recoil, and because we are working for a reactor neutrino which has maximum energy of 8 MeV, so the maximum nuclear recoil corresponding to is roughly 2 keV nuclear recoil, which is very small and hard to observe. So we are working with the detector which see ionization and doesn't see phonons. So to compromise it, we use quenching factor. So this is the quenching function with respect to nuclear recoil. So we are roughly at this region. So here by converting nuclear recoil to electron equivalent with the help of this quenching factor, what spectrum we expect is this one. So we have already achieved 300 eV threshold at 10 CPK background with liquid nitrogen detectors. And currently we are at this level at 200 eV threshold. And we are at around 10 to 30 CPK background in low energy. And with future detector, we expect to go even below and in the background and both in threshold. So how much counts should we expect with different threshold detectors is shown over here. So this one is the differential count and this one is the integral. And you can see that by going from 300 to 150 EV, the rise in count rate is exponentially high. So from here to here, it changes from roughly 0.8 to 27 counts per kg per kV per day. And this one is the latest spectrum of the current running G3 detector. And you can see we have secured roughly 200 eV, and we are just settling other noise, and we are doing pulse shape discrimination. So we are working on this even more. So the coherency in neutrino nucleus scattering is a main factor to discuss. And the coherency can be described with the form factor. So form factor gives a idea that how coherently whole nucleus moves during this scattering. And a general form of form factor can be given by this one. And most of the people use Helm model form factor, which used to be given by this expression here. For different model, the S and the value of R used to be changed, but in general, the form factor, you can see they have similar kind of shape, and in the low energy, they converge to 1. We have described the term coherency instead of form factor. We describe describe it in another way, and to describe coherency in this neutrino nucleus scattering, we consider the combined amplitude of nucleus with the term of protons and neutrons, and the total cross section can be given by AA dagger, and on calculating this one will get a term of 2 cos phi, where phi is the average misalignment angle between the nucleons. So this cos phi goes from 0 to 1, which can be defined as a degree of coherency. So as alpha goes from 0 to 1, the cross section goes from totally incoherent to coherent, and the cross section proportions to incoherent condition is epsilon square z plus 1, while in coherent condition it is epsilon z minus n whole square. This can be seen in this paper. So this degree of coherency is calculated for different target sources versus incident neutrino energy in this contour plot. And here we show it for three target nucleus, argon, germanium, xenon, and their isotopes. So you can see for reactor neutrino, here is the range to get the maximum coherency and maximum count rate. So it is always higher than 99%, but when you go from reactor to solar, it starts to drop, and it mostly drops for a stopped pion neutrino, and for atmospheric neutrino, it goes to its very low values. So we also defined one more parameter, the relative change in cross section from with respect to maximum coherency, which is given by Z here, and the change in degree of coherency versus incident neutrino energy for different target is shown in this plot. So here you can see for the low energy neutrino, the expected coherency is 1. As we go to higher energy neutrino, the coherency drops. But this is also, okay, sorry, this plot is just repeated somehow. Okay, so this one is for the detector threshold 0. So we also calculated how the coherency drops when we go from this ideal situation to the realistic one. So in that situation, we consider the minimum threshold is 0, while here we consider the detection threshold is not 0 and it's varying. So this one is for stopped pion neutrinos. And here you can see what is the expected count rate versus versus the nuclear recoil. And as high the detection threshold goes, the coherency changes, and which can be shown in here. So the maximum coherency can be achieved for these three targets is over here. So one can see that for xenon or CSI detectors, the coherency is rather low, up to below 70%. So this is the same for the reactor neutrino, and here you can see the coherency lies between the range from 100% to higher than 90%. And the same thing is for solar neutrino is shown over here. And for atmospheric neutrino is shown over here. So here you can see for atmospheric neutrino, which have spectrums roughly started above 50 MeV and goes up to GeV scale, the coherency factor is rather small. So this is the status of the neutrino nuclear scattering at Koshang Neutrino Laboratory. Here you can see the differential coherence effect versus the square of 3 momentum of recoil nucleus, and versus the form factor, and versus the ratio of cross section. All things are convoluted over here. So for the stopped pion neutrino, the coherency drops up to these ranges, and for the reactor it is as high as up to 96%, 94 to 96%, and for solar neutrino it is also as high as above 80%. So this is the current situation of our experiment. We are now at 200 eV threshold, and at the 200 eV we have already achieved a background of roughly 50 CPKKD, and if we have this much amount of data, then how much sigma we should expect to probe the neutrino nuclear scattering. So here you can see that with 100 kg days on and 45 kg days reactor off data, we should expect this black line, and which is below 1 sigma. So in order to go to high sigma values, we should either go to achieve low background, or we should switch to other detector, or get lower threshold detector. And by getting this one, you can see even at a high background with the same statistics, we can probe up to 3 sigma at 3 sigma neutrino nuclear scattering. So this is a summary of my talk. So neutrino nuclear scattering is important to study for electroweak interaction in standard model, and for irreducible background in dark matter searches and astrophysics. And studies of neutrino nuclear scattering is also useful for quantum mechanical coherence effect in electroweak process. And deviation from the maximum coherency can also be a probe for beyond standard model and form factors. And we have already achieved a threshold of 200 eV, and 150 eV is expected from near future detector. And we have the roadmap ready for reactor and solar neutrino soon. Thank you.
Okay, thank you very much for the talk. You did use up all your time, so I think we have no time for questions. Please use the chat in case there are questions, and we move directly to the next talk. The next talk is Implications of Rare Kaon Decays on Lepton Number Violating Interactions by Karel Friedel. Please.
Yeah, hello. I should share my screen. Yep. Okay, so I will speak about rare Kaon decays, and in the context of lepton number violating interactions. And this is based on work done in collaboration with Frank Tepisch and Julia Hartz. So neutrino masses are then a clear sign of physics beyond the standard model. And a well-motivated scenario to incorporate neutrino masses is for them to have a Majorana mass. And if the neutrino has a Majorana mass, then this implies lepton number violation, and which is interesting with respect to leptogenesis. So leptogenesis is a mechanism by which you can generate the baryon asymmetry of the universe, so the matter over antimatter asymmetry, first in the lepton sector and then transport it to the baryon sector. So with the lepton number violation in the neutrinos, there are scenarios in which this is possible. So experimentally, one very good way to look for lepton number violation is with neutrinoless double beta decay, for which you see a diagram here on the right, where the Majorana neutrino has a mass insertion here in the middle, and you have 2 electrons in the final state and none in the initial state. So this process violates baryon number by 2 units. The downside with this experiment is that you're only sensitive to the electron flavor of the leptons, and you're only sensitive to, if you treat this as a bigger operator, then you're only sensitive to the first generation quarks. So then we ask ourselves if there is any other experiment for which you could look for lepton number violation. And one of those is in the rare decays of kaons. So in the standard model, the K plus and K long can decay into a pion and 2 neutrinos. And the predicted branching ratio in the standard model is very well understood. And for this, you see the diagram here on the right. So we have the kaon, and the strange quark of the kaon interacts in this weak loop, and then you have the pion in the final state. And experimentally, there are currently running 2 big experiments that are looking for this. So it's the NA62 experiment at CERN, looking for the charged mode of this decay, and then the Koto collaboration at J-Park looking for the K-long decay. And they are both approaching these standard model values. So the future prospects of these kinds of searches is, they're interesting future prospects. And there are, on Tuesday, there were talks from both of these experiments by Marchevsky and Chimitsu, which you can now look at afterwards. So in the standard model, then you have a neutrino, antineutrino in the final state. But we can ask what would happen if you go beyond the standard model and say that you have 2 neutrinos of the same chirality in the final state, such that you violate baryon number by 2 units. What would the consequence of this be, and is it observable? So to go beyond the standard model, what we first do is to consider an effective field theory. So in the standard model, the lepton number conserving decay is a dimension 6 process because you have 4 outer fermions. And the beyond standard model decay that is lepton number violating would then be a dimension 7 process where you have an extra mass insertion from a Higgs boson. And in this EFT setup, the Lagrangian is expressed as a sum of different operators with corresponding Wilson coefficients, where then this Wilson coefficient is proportional to 1 over new physics scale to the power of the dimension of the operator minus 4. So if you have a larger dimension operator, you will have a larger number here. And in this new physics scale, we encode all the effects of the heavy new physics. And the most studied operator is the Weinberg operator here shown as O1, which can mediate the rare kaon decay. So here you see the S quark becomes a D quark at this long range interaction, but it's suppressed by this GIM loop. And therefore, we expect its effect to be small, maybe compared to this dimension 7 operator called O3b here, which can mediate the decay directly. So we choose to study this dimension 7 operator. And the prospects of detecting lepton number violation can be studied in terms of the momentum distribution of the decays. So in the 6-dimensional standard model decay, it's mediated by a vector current, while if it's a lepton number beyond the standard model decay, it would be mediated by a scalar current. And so the distribution in kinetic energy depends on what kind of current you have in the decay. So here on the right, there's a plot showing what it will look like in an old experiment, the E949. The standard model distribution versus the lepton number violating distribution. So you see that the lepton number violating distribution peaks earlier. And in these shaded areas here, we see the 2 signal regions of the experiment. Now you see from the graph, we have normalized the blue and the red curve to have the same area or the same area under the curve, but where the signal regions are, you expect more events from the lepton number conserving decay. And therefore, the branching ratio that the E949 experiment puts on the vector decay is more stringent than what it puts on the scalar current by quite a lot. So there is a big difference in the what the different currents you have in the experiment. And the dashed lines here are what it looks like at the experiment after they have made their cuts. So we see that the lepton number conserving decay mode is expected to be more apparent here. Now looking at the current experiments, we have the Koto experiment. The same kind of story happens here. So we have the standard model decay peaks more in the signal region than what the lepton number violating decay does. Here, the distribution is with respect to the transverse momentum of the pion. And for Na62, it looks similar. So where they have put the signal regions, you also expect more events from the standard model decay than for the lepton number violating decay. And here on the right in the table, you see just by taking the amount of phase space that falls within the signal regions, what kind of percentage of the total phase space that you can see in the experiments. So here at Na62, you can see you barely would get any events in the signal region 1, while in signal region 2, it would be kind of equal between the two. For the old E949, it's kind of the same story. And then for the Koto, you expect more standard model events. So also for these experiments that have two signal regions, then you would expect more in one signal region or the other, depending on the type of current. This might be a hint towards either lepton number violation or lepton number conservation if there is a significant number of events, but a proper statistical study would be needed for this kind of analysis. Furthermore, for the Na62, they make cuts also not only in the S, so what I showed before was in the S cuts, where S is the missing energy, so the difference in the energy of the kaon and the final pion squared. They also make cuts in the pion momentum, and we see here in these plots that even if they make the pion momentum cuts, the behavior stays the same. So really, in this experiment, we expect more events in the signal region 1 than in the signal region 2. Now, the way that this could maybe be used is to look at how many events you actually see in the different boxes. So this is a figure that was shown then on Tuesday in the presentation by Marchevsky on the behalf of the Na62 collaboration, where they have now reported 17 events at the Na62 experiment, where they, so I mean, based on counting the number of events in the different signal regions, then if a proper statistical analysis is done, then something could be said about the current. And I put here the link to the talk in case you want to see later. So if this operator is realized in this KM case, it will also lead to other consequences. We would have a radiative neutrino mass maybe, and it could induce neutrinoless double beta decay. But for the neutrino mass, this mass generation depends highly on the type of UV completion you have to the effective field theory. So there could be non-trivial corrections to the neutrino mass, and therefore this does not put as much of a stringent limit as the direct experiments such as the neutrinoless double beta decay. But this decay is only sensitive, like we said, to the electron neutrino and to the up-down type quark. So the kaon decay is like a complementarity to this. Now, as a consequence for the leptogenesis, so like I said earlier, the lepton asymmetry can be translated into a baryon asymmetry. And if you have a lepton number violating process active in the early universe, it can act to wash out a previously generated asymmetry. So if you generate the asymmetry at some high scale, and we assume that the operator in question is active after this scale, then you can act to wash out the generated asymmetry. And it's possible to calculate based on this, the scale of the new physics, how strong the washout is and to what extent it's active. So by comparing it to the observed value today, we can get a feeling for when the washout should stop. So it's interesting to find these scales. Now, using the experimental limits from the Koto and the Na62 experiment, we can get an estimate for these scales. So what we do here is take the experimental value to be the sum of the standard model plus maybe some contribution from lepton number violating interactions, where for the lepton number violating interactions, we account for this difference in the phase space that the experiment is able to see. Based on this prescription, we find the new physics scale of order 10 TeV for both the Na62 and the Koto experiments. And these new physics scales lead to washout scales very close to the RHIC symmetry breaking. So we would assume a strong washout from order 10 TeV to order 100 GeV. And therefore, if these operators are found then in the kaon decays, they would put very stringent constraints on the high scale leptogenesis. So if you generate the asymmetry at a high scale, you would have this washout if these operators are observed, and therefore it's very hard to explain these kinds of scenarios. So to conclude, we find that the distribution difference between the scalar and the vector current in kaon decays is significant. And if proper statistical analysis is performed, it may be possible to distinguish the or get hints of whether the excess, if an excess is seen, it may be possible to guess whether it's lepton number violating or lepton number conserving. And if an observation of these kinds of operators are made at the rare kaon decay experiments, then it would put the high scale leptogenesis under significant tension. So thank you, that was it.
Okay, thank you very much for the talk. We have time for a quick question. If there is a question, please raise your hand. So maybe I can ask a question. So I understood that you are looking at the kinematical distribution of the event. So in what sense is this a proof that there is really lepton number violation? Because I think you're not observing directly any lepton number.
No, exactly. So in this kaon decays, what you're observing in the final state is the pion. So you're not observing the lepton number, you're not observing the neutrinos themselves. So they are treated as missing energy in the experiments. Now, if you only have missing energy, it's hard to tell what kind of energy this is, but in the standard model, it's neutrino antineutrino. So what we do is to see what would happen if it was neutrinos, two neutrinos of the same kind, such that the decay would be lepton number violating by 2 units. And then from these dimension 7 operators, you would get a scalar current rather than a vector current. And therefore, with a scalar current, the distribution is different in the pion momentum. So then you're still only observing the pion, but based on the statistical distribution of the momentum of the pion, it could hint whether or not the new physics contribution is by a scalar or a vector current.
Okay, thank you. So I see no further comments, so let's move on to the next talk. Next talk is by Studenikin about non-standard interactions in radiative neutrino mass models. Please, can you share your screen?
Yes, yeah. Can you see my screen?
Very good. Yes, looks good. Please.
Okay, thank you for giving the opportunity to talk about a non-standard interaction in radiative neutrino mass model. So this is based on this my 2 paper in collaboration with Professor Babu and Anil and Bhupal, and another one with Yukong. So this will be my brief outline. First, I'll talk about basic radiative neutrino mass generation mechanism. Then I'll go to non-standard neutrino interaction, and I'll summarize the prediction in this radiative model. Then I'll conclude. Yeah, and as we know, like neutrino mass is one of the concrete evidence like that leads to go beyond the standard model. But in standard model, neutrino mass is exactly 0 due to no presence of right-handed neutrino. If you write down the some u-car times electroic wave and it introduce right-handed neutrino, still the u-car you need to take like very tiny. It is technically natural in tube sense. And that means like if you set MF to 0, then you go, it's delta MF goes to 0, which is technically natural, not like the Higgs case. Anyway, so 2 ways basically you can generate this neutrino mass. One is integrating out the heavy state, and another way is the quantum loop correction. And there will be some 1/16 pi square to the power n. If you go higher and higher loop, your new physics scale can be much lighter. So here I'll focus on the radiative neutrino mass generation. Because like in radiative neutrino mass generation, your new physics scale can be naturally arise at TeV scale due to this loop suppression, as in some cases there will be chiral suppression. So, so new physics can be at TeV or sub-TeV scale very naturally. So in these models, neutrino masses are 0 at tree level, and technically you do not need any right-handed neutrino. You can generate the Majorana mass term at the quantum level. Typically, new heavy scalar fields are introduced while its lepton number. The simple realization is the G model. Okay, so in this work, actually, we classify in based on non-standard neutrino interaction, like all these radiative models into two categories. One is type 1 radiative mechanism and type 2 mechanism. In the type 1 radiative mechanism, we are classifying those radiative neutrino mass models which has at least one standard model particle in the loop. Then in that case, you will have both, as you can see, there will be both chiral as well as loop suppression. So, and in this kind of model, there will be some non-standard neutrino interaction prediction. And these are obtained from effective dimension 7, 9, 11 operators from the selection rules. And if the loop diagram has at least one standard, as I said, like this can be cut to generate such effective operators. And this is classified in Babu and Leung's paper in 2001, and there is a review on that also. But what about type 2? Type 2 is like when, if you see, like inside the loop, there is no standard model particle in the loop. So in the earlier case, there are some finite possibility, but here you can have any particle in the loop and you can build any neutrino mass model. But the thing is that in this type of model, you will not generate any non-standard neutrino interaction. So these we are categorized in type 2. The simple example is a scotogenic model, which is proposed by Ma, and there is some dark matter candidate and stuff. But this type of model doesn't generate any non-standard neutrino interaction. Okay, so new physics near TV scale for the non-standard neutrino interaction, like it can generate some NSI, and which can affect basically in neutrino production, propagation through matter, and detection processes. And the most important effect of NSI is in neutrino propagation in matter. So you can write down this operator in like effective operator like this. I'm not going in detail. And you can write the matter potential. You can see this is 1, this is coming from the standard model W interaction, and the others are non-standard neutrino interaction entry. Diagonal and non-off diagonal entries. So these NSIs are of great phenomenological interest. There are lots of literature in it, like in phenomenological study, defined experiment, as these will modify scattering experiment as the production and detection vertices are corrected. Presence of it may affect the mass ordering and CPU violations. But however, like there are relative lesser effort has gone into how we can realize this kind of NSI in the UV complete model. The major challenge is to generating these observable NSI in UV complete model is the charge lepton flavor violation, because also there's some low energy constant will not restrict you to generate this kind of large non-standard neutrino interaction. So here I'll give some example like how you can generate NSI in some UV model. So simple model is the G model. One of the simplest model is the G model in radiative model. So gauge symmetry is exactly like standard model. No harmonic extension. You have 2 doublet and 1 charge singlet. And this is the Yukawa Lagrangian. I'm not going. So if you see the neutrino mass diagram, this side there is this eta plus is the singlet one, and H2 plus is coming from the doublet. The 2 Yukawa, in the left side Yukawa is termed as F, and the right side Yukawa is Y. If you import G2, then the model is ruled out because you cannot generate the proper flavor structure. This is the Wolfenstein version. Because the other case, if since this is charge singlet, the Yukawa texture will be antisymmetric, so you cannot generate neutrino flavor structure properly. However, Y needs not to be proportional, like exactly diagonal. It is general because it is coming from the doublet. And NSI arises via this exchange of these 2 charge scalar. So like this. Exchange of this single charge scalar from singlet and the doublet. But one thing I should mention, for the singlet case, if I take this FU cover to generate non-standard neutrino interaction, you have to have this first column has to be large value. I'll later show that. And for the singlet case, I cannot turn on large U-cover because that will induce the off-diagonal entry, other entry also. So it leads to large lepton flavor violation. So what we are doing, setting F to be tiny, U-cover, you can turn on large, then you can get some large non-standard neutrino interaction. As you can see, there are 4 diagrams, but some of them are proportional to Y U-cover and some of them are F. These we are neglecting because anyway, if you enlarge, it will be tightly constrained. So here I am showing the proportionality of the U-cover for different like flavor diagonal and off diagonal NSI, and this is the NSI expression in the G model. And I show in the blue color which are responsible for the generating non-standard neutrino interaction. So to generate the large non-standard neutrino interaction, we have to face several constraints. Like one of the main constraint is charge breaking minima, because it is coming from this two charged Higgs mixing. If you turn on these cubic couplings to be too large, it can happen that there could be some charge breaking minima you can develop. So you need to ensure this charge conserving minima is deeper than the charge breaking minima, and that will some limit that put some limit on this sin phi, and that I am just passing. Also from electroweak precision constraint, where because this the doublet, if you two consecutive members you are turn on large mass splitting, then you will it will contribute to T parameter, and you have to be consistent with that. So allowing 2 sigma, I'm showing the what is the allowed value of sin phi in different range for different mass value of this heavy charged Higgs and the neutral Higgs. This is the same figure, just I'm zooming in. So for suppose say the heavy Higgs to be 0.7 TeV and light charge Higgs to be 100 GeV, the maximum mixing you can get 0.63. Okay, so another constant you have to face, as earlier I mentioned, lepton flavor violation. The FU cover we are not turning on large, and here we are playing one interesting thing. As I earlier mentioned, this YU cover, if you see, this is completely 9 entries are completely free. But the lepton flavor violation, lepton flavor changes along the row, neutrino flavor changes along the column. If I turn on large entry along the column, which is not dangerous. So if 2 entry in a single row is not very large, then it is fine. You can satisfy the lepton flavor violation constant, and that is the trick we are playing. And also we are considering this constant from the lepton flavor violation. Similarly, for trilepton decay, also in terms of this Yukawa, which is responsible for NSI, we are putting some constraint. Also, then you can ask, like, there should be some direct and indirect searches of this type of charge scalar. Yes, so there could be some, since it is coming from the, like the charge scalar, which is coming from the doublet, there is some neutral scalar, which can lead to late contact interaction E plus E minus to L plus L minus. From that, that will also impose some constant on the Yukawa and mass plane. And there is some charge Higgs searches at LAB, LAB as well as LHC. Most of the searches mimic like exactly lepton searches or the other supersymmetric searches. As you can see, you can produce in H channel H plus H minus, and then it goes back to L neo or T channel process or in association with W. And we are taking considering all of these constant, and we are putting constant in the plane. So for simplicity, we are not considering any, we are trying to avoid any stringent limit from ion decay. So we are considering branching ratio of E nu and tau nu to be 1. In that plane, you can see all these constant selectrons, muon, and tau from left constant, as well as some LHC constant is there. We are the left y-axis is branching basically to tau nu, and right y-axis is branching basically to E nu. You can see like a 100 GeV charge scalar, which is consistent with all the constant still. And also we consider in this case there will be some deviation in tau lifetime or tau universality. We are consistent. So also there will be some other constant, like if you have some charge scalar in that light scale, it can affect some Higgs observable, which leads to gamma gamma. So those constant also we are taking care of. And there could be some from the cubic coupling, there will be some almost H2WW star signature, which will mimic like H plus minus H plus minus plus star. And this is three-body decay. And that's kind of, it can hide under the WW star type of signature. So after considering all of these constants, you can see like still I can get for if psi EE as big as 3% in this type of model, if some mu 3.8%, or if psi tau tau to be 9.3%. And in all of these cases, we are considering some Borexian scattering experiment limit, as well as the we are taking this from this global NSI limit on oscillation, considering oscillation plus coherent thing. So, and these are some DUNE projection which can be probed. So you can see still 9.3% NSI is achievable in this type of model. But however, for the off-diagonal NSI, the scenario is very worse because you cannot get from the lepton flavor violation because it restricts you if some mu tau maybe maximum 2.5% or if e tau 2.5%. But which is not, that's
so you have 1 minute left.
Okay. Yeah, I mean just, also we check whether this is consistent with the neutrino oscillation data or not, and yeah, we are fine with that. And for the where we are getting large NSI, we check whether we can get neutrino prediction or not, which is consistent. And I will mention here just one more point. If you have some charges in this light scale, that can look like a Glasso resonance at ICHEP that we have analyzed. And if you see for the W boson case, it can pick up at like 6.3 PeV, but in this case, 100 GeV type of scalar, it would show up like this, which I'm showing in blue type of peak, which can be a different kind of probe of NSI in the ICHEP. Okay, so I'm not going in detail of the other model we have done for the other radiative models also, like leptoquark models, and here I'll just summarize. So, so based on these models, actually, whatever the NSI you can get up to, just depending upon this type of charge scalar or leptoquark, whether it is coming from singlet, doublet, you can generalize the statement to what the maximum NSI you can get up to. So this is the summary of all of these models. So the conclusion is matter NSI in the radiative neutrino mass model has been studied. Mass as low as 96 GeV charge scalar is shown to be consistent with direct and indirect limits from LEP and LHC. Some sizable NSI you can achieve in these radiative models. And radiative neutrino mass models allows parameters which are in good agreement with the neutrino oscillation. Thank you.
Okay, thank you for the talk. We have to move on to the next talk, so please pose any questions you have in the chat and the MetaMost channel, and we directly move to the next talk, which will be on anti-neutron oscillation search with MicroBooNE and DUNE by Yeon-Jae Jwa. Yes, we can see your slides.
Can you hear me
Hello?
now?
Yes.
Oh, sorry. Hi, I'm Yeon-Jae. I'm a PhD candidate at Columbia University. Today, I want to talk about neutron to anti-neutron oscillation search with a liquid argon time projection chamber on behalf of the DUNE and MicroBooNE collaborations. So I will give the theoretical motivation for neutron anti-neutron oscillation and experimental searches. Then I will introduce machine learning based analysis method in liquid argon time projection chambers. Then I will discuss future bound neutron anti-neutron oscillation search in DUNE. Then I will discuss ongoing analysis validation in MicroBooNE. So first of all, NMR oscillation is a process where neutron spontaneously converts itself to anti-neutron. It's a baryon number violating process, and BNV is one of Sakharov's conditions, which makes it a necessary condition for matter-antimatter asymmetry in the universe. And NMR oscillation is predicted by a number of Bjorn standard model theories. So there are two branches in searching for NMR. The first one is NMR search in free neutrons. The other one is NMR search in bound neutrons, which I will be focusing on during this talk. So here we look for anti-neutrons annihilation signature in a nucleus. The bound NMR lifetime is related with the free NMR lifetime by the through the internuclear suppression factor with this formula. The suppression factor for argon specifically was recently calculated to be this value. Super K holds the current best limit for the NMR lifetime in the oxygen bound neutron, which is 3.6 times 10 to the 32 years. This is equivalent to 4.7 times 10 to the 8 seconds for free NMR lifetime. So NMR signature often contains multiple pions in the final state. In argon, NMR oscillation is followed by the annihilation with a nearby nucleon. So N-bar N and N-bar P pair mainly generates multiple pions in the final states. And the outgoing particles momentum sum should be close to 0, and the total energy release should be close to the two nucleon mass. And the topology of the K product has a spherical symmetry with high pion multiplicity. So we call this an NMR star-like or pion star signature topology. So in the figure, I'm showing the discovery figure of antiproton, but the NMR oscillation signature is very similar with this. So LAR-TPC technology is shared by MicroBooNE and DUNE experiments. LAR-TPCs have millimeter scale wire resolution, and it has also very good calorimetric resolution. So this is very well suited for capturing and identifying the signal topology. So here I'm comparing NMR search in DUNE or MicroBooNE. For DUNE's case, it's deep underground and it's well shielded from most of the cosmogenic activity. The anticipated background process is high energy atmospheric neutrino interactions. The exposure will be 4 times 10 kiloton TPC volume for the duration of 10 years. And DUNE assumes self-triggering on rare events like proton decay, NMR, and atmospheric neutrinos. On the other hand, MicroBooNE is on-surface operation. So the dominant background is the constant stream of the cosmic ray muon tracks. The size of detector is about 80 ton. So it's about 500 times smaller than DUNE. And we are expecting factor of hours of exposure, and it uses a random trigger for off-beam readout. So here I'm showing the overview of this machine learning based analysis flow. So this analysis combines traditional reconstruction with the image classification. So the boosted decision tree takes traditional reconstructed kinematic variables and CNN image classification score obtained from the convolutional neural network. And the final BDT classification is used at the final selection. Alternatively, CNN only classification and BDT only classification without the CNN input is also possible. So now let me talk about NMR search in DUNE. Here I listed input BDT variables. The bold-faced ones can be found on the left-hand side figures. So you can see the signal and the background distributions for the number of tracks and number of showers and total visible energy and the CNN score. And the final selection uses an optimized combined BDT cut. Using this cut, 8% of signal efficiency with the 0.02% background efficiency was achieved. Using this selection to the 400 kiloton years of exposure, about 20 background events are expected and about 30 signal events are expected when bound neutron anti-neutron oscillation lifetime is assumed to be the current best limit coming from the super K measurement. In calculating the 90% CL sensitivity in DUNE, the exposure and the signal efficiency and the background counts are needed, then the Bayesian posterior distribution for the decay width is can be found as Poisson distribution in combination with the Gaussian priors of these variables. Then the 90% of the decay width, gamma 90%, can be achieved, can be obtained from this equation. Then the NMR lifetime sensitivity is given by 1/gamma 90%. So the 90% CS sensitivity for argon-bound NMR lifetime is achieved at 6.45 times 10 to the 32 years. This translates to free NMR lifetime of 5.53 times 10 to the 8 seconds. This result is comparable or slightly better than the current best limit at super K. The effort on further improving the analysis and the sensitivity is ongoing. So while MicroBooNE isn't gonna provide the competitive limit in searching NMR, but the method can be validated on the MicroBooNE. So on MicroBooNE simulations, the CNN only, BDT only, and combined methods has been demonstrated. Here, signal efficiencies at 62.3, 90.5, 90.7% for BDT only, CNN only, and combined method were found at 95% of the background rejection. And a small subset of the MicroBooNE run-on OFIM data was used to validate the CNN only and BDT only method. The OFIM data is expected to follow the CNN BDT responses of the cosmic Monte Carlo because we assume negligible amount of NMR signal can be expected in the data given the existing limit. So, however, data Monte Carlo disagreement is pretty evident. It's understood to be due to imperfect modeling of cosmic flux and or detector response. So this clearly illustrates the challenge in applying Monte Carlo techniques trained on neon simulation. So improvement of the analysis targeting data Monte Carlo agreement is ongoing. To summarize, the future DUNE experiment is well positioned to provide the world leading sensitivity for NMR oscillation. MicroBooNE, sharing the same technology as DUNE, is prepared to provide the stage for a proof of principle demonstration of ML-based analysis methods and the first LRTPC-based search for NMR oscillation, and further improvement in data Monte Carlo agreement for the MicroBooNE analysis is ongoing. Thank you for listening.
Okay, thank you very much for the talk. We have time for a question. Please raise your hand if you want to ask a question. Okay, I don't see any hands up. Okay, so thank you again, and let us move to the last talk of the session. The talk will be by Leigh Howard Whitehead about neutrino event reconstruction in DUNE using Pandora.
All right, let me just pull up my screen.
Yes, we can see the slides.
Great, let's put my video on as well. Okay, well, we ready to go?
Please, yes, please start.
Okay, well, I'm Leigh Whitehead, a senior RA at University of Cambridge, and it's my pleasure today to talk to you about neutrino event reconstruction at DUNE using Pandora. So I'll just briefly give an introduction to DUNE itself, and then Pandora, and then give some results from the reconstruction performance that we have for the far detector at DUNE, as well as one of the prototypes, and then finish with a few concluding remarks. So DUNE's a next generation long baseline neutrino oscillation experiment. It has a wide physics program. Clearly this includes many parts of neutrino oscillations, from the measurement of CP violation and the neutrino mass hierarchy, and high precision measurements of the neutrino oscillation parameters. Beyond that, we heard in the last talk about baryon number violation searches, and also supernova neutrinos, sterile neutrinos, and many other things. So in terms of the neutrino beam itself, it's produced in a Fermilab in Illinois. It'll be a high power neutrino beam that passes through a suite of near detectors also located at Fermilab before the neutrinos travel 800 miles, or about 1,300 kilometers, to the Sanford Underground Research Facility in South Dakota, where they will be detected by 4 10-kiloton fiducial liquid argon time projection chambers, or LAR-TPCs. In this talk, I'll focus on the single phase design for these TPCs, where we get 3 views of each neutrino interaction from the wire readout planes. So for single phase liquid argon TPCs, the entire detector is fully submerged in liquid argon, and they're reasonably simple in design, in that we have a cathode held at a very high negative high voltage, such that we can set up an electric field of 500 volts per centimeter from the cathode to the anode. The anode itself is made up from 3 wire planes, shown here. So the vertical lines here, the purple wires are the so-called collection plane that actually collect the charge
and the green and blue planes are angles to the vertical induction wires that get an induced charge on them. So when the ionizing particle comes through, it ionizes the argon, and the ionization electrons drift in the electric field to these readout planes, and we get signals on the 3 different wire planes. So at the end, we see events in the 3 views, as you can see on the right-hand side, in these green, blue, and purple boxed images. So Pandora is a software development kit for automated event reconstruction. It was originally designed for the ILC, but in the last few years, it's now been applied to a number of liquid argon TPC experiments, particularly neutrino ones. It's a collaboration between a number of UK institutes, and including Warwick, Lancaster, and Cambridge, but we're all always open to new members and collaborators for this project. And within the UK, Pandora has a long-term plan funded for 7 years for developing the event reconstruction for the JUNO file detectors. So Pandora is a software framework to facilitate a multi-algorithm approach. And by that, I mean, we want to break down the event reconstruction problem into many small steps, so that each step in the reconstruction is therefore incremental and focused on a very specific task. And the aim of this is to avoid making mistakes, because any mistakes you make in event reconstruction are typically very hard to undo once you've made them. And using this methodology, as the event develops and we start building up the particles, we can then employ more sophisticated techniques and algorithms. So we have over 100 algorithms and tools. I think it might be over 150 now. And these vary from kind of simple cluster-based pattern recognition, what you might call traditional techniques, and we use those where they work well. But we're also now implementing machine learning and deep learning approaches at kind of key points within the reconstruction chain. And these algorithms have kind of physics and detector knowledge built into them to optimize the way in which they work. So whilst there are these large number of algorithms used, you can basically break down the reconstruction process into 6 main steps. So on the left here, this is just one of the wire plane images like we saw a few slides back, where we just have the hits shown in gray. An example of including the detector geometry information is shown here. This is a gap between 2 of the drift volumes. So the first thing we do is some basic 2D clustering to kind of group together hits that are locally matched with their neighbors. And from this, we can start building up small clusters, as you can see, and each cluster in a different color here it is an individual object. So we can then start grouping these clusters together. So in the right-hand side of this figure 2, you can see that we've already built up these nice track-like structures, at least in this 2D view we're looking at. And there are still some fairly sparse clusters that correspond to the shower-like particles. We then try to form vertices in 3D. We do this vertex finding quite early on in the reconstruction because it really helps to guide the kind of particle flow and the development of the event. And so once we have that, we can then kind of move to the more 3D parts of the reconstruction. Sorry. I seem to have lost the ability to change my slide. Sorry about this. Sorry about that. So once we get to the kind of 3D part, the first thing we want to do is to match our views together. And since we have 3 views, we can match these together in a way that we do it pairwise. So
in this example on the left, we have the U and the V clusters corresponding to the shorter of these two tracks. And if we match these into 3D and then project back down onto the third view, we get this blue cluster, and this blue cluster is completely overlaid on the position of the actual cluster in that third view. So we know that we've made a good match there, and we've paired together the correct clusters. So at this stage, we now have in the center here, we've started building up our particles, and we can kind of switch back between 2D and 3D to help refine this particle creation. But at this stage, again, you can see that the tracks have been fully reconstructed there in red, and the showers are now being reconstructed with these kind of seed positions, as well as some smaller outlying shower branches that will be added on later. So we then have these kind of initial particles in 3D, and then finally we group together these final remaining hits for the showers and end up with our fully reconstructed event in 3D, where we have these two tracks and two main showers. And if you can zoom in right at the vertex, you can see that there's also a couple of short tracks just at the interaction point at the bottom there. And so at this stage, we have our kind of full particle hierarchy. And all of this Pandora reconstruction for the FAR detector has been benchmarked in the JUNE technical design report. There's a link to it at the bottom of this slide. And so just a couple of highlights from there. So this is the particle reconstruction efficiency from a kind of mixture of nu mu and nu e interactions. So on the left, we have the track-like particles, so namely muons, protons, and pions, as a function of the number of hits, and below the true momentum. And you can see once we get above a few tens of hits, then we have very high reconstruction efficiencies, over 90%. And on the right-hand side, corresponding plots for the shower-like topology particles, so electrons, positrons, and photons. And again, once we get above a few tens of hits, the reconstruction efficiencies for these particles is very good. Similarly, the neutrino interaction vertex resolutions shown here. The plot on the bottom right shows the kind of the three-dimensional distance from the true vertex position. So roughly 68% of the time we're within 1 centimeter of the true vertex position. And the three other images here just show this resolution kind of projected out onto the three spatial coordinates. So moving to ProtoJune now. So the single phase ProtoJune detector is a prototype of JUNE at CERN. It's located in a particle test beam, and its surface location means it has a very large cosmic flux, which is a different challenge to what we'll see at JUNE. In any case, the detector consists of 6 different readout planes, but they're arranged to 2 drift volumes. And there's a central cathode that divides the detector in two into these two drift volumes. So Pandora is the primary event reconstruction we use at ProtoJune single phase, and the outputs of this reconstruction are used in a large number of analyses. The figure here shows a reconstructed beam event from our simulation. So the bottom 3 plots are the 3 views we see from the detector, and the beam particle is the kind of dark blue one entering at the bottom of these figures. So it comes in and has some fairly catastrophic interaction and makes a number of particles at this point. And at the top, you can see the kind of zoomed in image of the particle in 3D. This beam particle hierarchy buried within the large number of cosmic rays. So we have a good feedback loop from analyzers to help these developments. And one specific development that we had to make for ProtoJune is the so-called track stitching. So this is where we put together the reconstructed objects on either side of the cathode. And in doing so, we can measure the arrival time of our cosmic rays. And so the plot on the right here shows the reconstructed time distribution as a relative to the beam trigger for our cosmic rays in both data and simulation. And you can see more about this in the ProtoJUNE performance paper that's now been posted to the archive. So finally, we have new developments ongoing, mostly with regard to the FAR detector, but these will also improve things for the other detectors too. The integration of deep learning techniques, particularly convolutional neural networks, increasing the use of charge information. There are quite often times where trying to do the particle reconstruction just geometrically has ambiguities in it, and charge can help us resolve these issues, particularly for the dual phase detector, for example, that only has 2 readout views. And finally, high energy muons. These are very important for the calibration for the FAR detectors due to the deep underground location. So in summary, Pandora's performing well for DUNE and ProtoJUNE single phase. We're also supporting the dual phase ProtoJUNE, which I didn't have time to discuss here. And these improvements we're planning will be benchmarked against our FAR detector simulations, as well as the ProtoJUNE data where possible. And we also have a strong intention to support the event reconstruction at the near detectors and the various different detector technologies that involves. So thank you very much.
Okay, thank you for the talk. We have time maybe for one quick question, if there is any. Okay, I do not see any questions. So yes, I would like to thank all the speakers of the session. We can conclude now the Neutrino parallel session. I think the chat in MetaMost is still active for some time, so there is still opportunity to discuss.
There should be one more talk, Thomas. There's another talk from June.
Oh, I'm sorry. I'm sorry. I don't see it in the program. Okay, I'm very sorry. I apologize.
I can go ahead and share my slides.
Okay, many apologize for that. I didn't see it in the program.
No worries. Can everybody see my slides?
So let's have the final talk about deep learning event reconstruction, DUNE, by Ben Jaworski. Please.
So my name is Ben Dragowski. I'm a PhD student at University of California, Irvine, and I'm just going to be quickly going through some of the efforts towards deep learning-based event reconstruction at DUNE. So as you knew, DUNE is a long baseline neutrino experiment. One of its main goals is to measure neutrino oscillation parameters. But good measurements of these parameters need both good energy resolution and also good event classification efficiency. And those are both pretty central to good measurements of the oscillation parameters. So events at DUNE, in DUNE's large TPC will leave behind ionized electrons, which will float into three wire planes, 2 induction planes and 1 collection plane. For each plane, by using the wire number and the drift time after the event, you can have 3 images for each event. So to see what that looks like, you can look at a new ECC event here, a simulated one. So for each event, you get 3 different views, 2 induction planes, 1 collection plane. The x-axis is the wire number for these, and the y-axis is the drift time. So for each event, now we have these 3 images, and since we have 3 images that kind of sum up the event, it's an ideal application of CNNs, which are specialized neural networks that take in images, and they use a set of filters which translate across the image, and they can find useful characteristics of the image. But what are we actually going to do with these CNNs? So broadly, there are 2 different things you can use CNNs for. One is regression, the other is classification. So for regression, you'll output a real number or a list of real numbers. And this is what you'll think of for things like particle energy, event energy, or event vertex. So the other is classification. So for that, if it's binary classification, it'll output a number between 0 and 1, showing how likely it thinks it's in one of the two classes. But you could also have an arbitrary number of classes, and in that case, it'll output that arbitrary number of numbers between 0 and 1. And this is useful for things like particle ID or event ID. So what I'll talk about in this talk is first I'll start out on energy regression, specifically for event energy, and then I'll look at event classification. And then lastly, I'll just have a quick look at other more novel methods being developed. So just as an idea for what the architecture of the regression CNN looks like for events, the main takeaway is it takes in 3 images. On each of those images individually, it has some convolutional layers and some pooling layers. Then it concatenates each of those 3 smaller sub-CNNs, and then has some more convolutional layers, and then outputs an estimate for energy. So we have an architecture. The standard architecture is based on ResNet. We need to pick a loss function, which tells the CNN how close it is to the truth. So for that, we choose a mean absolute % error. We choose this instead of a square of errors, so that it'll be more robust to outliers. We also apply a weight in the loss function. So events in regions of true energy that are less populated will be given priority, so that what the CNN will actually see is a flat distribution of true energies. And this will make it so it won't be more inclined to say, just guess the most popular value of energy if it's not sure what to do. So now we take this architecture and we train it first on new ECC events. The plot shown here is reconstructed energy minus true energy all over true energy. So in that plot, there's the blue, the regression CNN results, and these are contrasted to the traditional kinematic-based energy. The kinematic-based energy is found by adding up leptonic and hadronic energy components individually, and each of those components are found by adding up the calorimetric energy and then applying an overall factor. So you see the CNN-based approach has a pretty big improvement in resolution. It's around 8% compared to the traditional methods, 13%. So the overall resolution is better, but we're also interested in the resolution and bias at particular values of true energy. So here I bin the events by values of true energy, and then I look at the mean of the resolution to the left and then the RMS to the right. And again, the red is the traditional and blue is CNN. So you see that looking at the RMS on the right, you see that the CNN keeps the edge over the traditional method over all ranges of true energy. And the bias is comparable for both of them, but the CNN is slightly better near lower energies. It's also interesting to break up the interaction types. So at DUNE, we don't just have quasi-elastic CC events, but we also have several other interaction types with non-trivial hadronic components. So here we're breaking up the events by those interaction types: quasi-elastic to the left, deep inelastic scattering in the middle, and then resonance to the right. So you see that it has very robust performance over all these different interaction types. And this is a pro of using a CNN, as the high number of degrees of freedom allows it to learn all these interaction types very well. So we've seen the results for new ECC events. Next, we're going to look at new mu-CC events using the same architecture, just now training it on new mu-CC event energy instead of the new ECC energy. So Again, looking at the resolution, we see the CNN method has a boost in performance from the traditional's 19% resolution to around 12.5%. So it's a big boost. Here, again, the traditional method, the kinematic method, is just based on adding up the leptonic and hadronic components. But for new mu-CC events, the muonic energy is calculated based on the muon track length instead of the calorimetric charge. So next, we move on to event classification. So the network was developed to classify events as either nu-E CC, nu-mu CC, nu-tau CC, or neutral current. So here we're looking at the results for nu-E CC classification. The FHC, mostly neutrino beam, is on the left, and then the RHC beam configuration is on the right. So it outputs a number between 0 and 1 for each event. 0 means it's not likely to be nu-E, and then near 1 means it is likely to be nu-E. And for the analysis, the cut is on 0.85. So if the classifier is 0.85 or higher, it's chosen to be a nu-E CC event. So now looking how this efficiency looks, we can break this up into compare the efficiency to the reconstructed energy. So the selection efficiency over the range of reconstructed energy is shown here. It's that solid black line, and that's shown up against the neutrino flux, which is that cyan shape. So you can see near the flux peak, you have around 90% for both of them, 90% selection efficiency. It's slightly better for the anti-neutrino beam just because the difference in interaction types. So now we can look at the same characteristics for the nu-mu CC interaction score. So similar as before, now it's just classifying it as nu-mu CC. Again, the FHC is to the left, RHC is to the right. So now we call anything with the classifier score greater than 0.5 as a nu-mu CC event. So now showing the selection efficiency for nu-mu CC events. Again, it's greater than 90% at maximum for both of them. Again, a little bit higher for the anti-neutrino beam, just because the difference in interactions. And so lastly, just want to mention some other methods. So one method that seems promising is sparse submanifold CNNs for semantic segmentation. So if we want to reconstruct 3D points for the hits and put it in a 3D pixel map, the issue there is that it's a 3D pixel map, so computationally it's much more difficult, and most of the pixel map is going to be empty. So that's the advantage of using a sparse submanifold CNN, is that it's a specialized algorithm for being applied to sparse data that takes advantage of the fact that most of the pixel map will be zeros. And so this has been shown useful for identifying individual pixels in the pixel map as part of, say, a given track or shower. So the other novel method I wanted to mention is graph neural networks. This isn't a type of CNN. It's somewhat related, but different. So this, instead of breaking up all the hits into a pixel map, what it does is it breaks up these hits into a graph, which is comprised of connected nodes. Each one of the node will have information, say, about position or the energy decomposited or composited at that hit. And so then we take this abstract graph, and this is what we feed to the graph neural network. And then it can label these individual nodes, which are actually hits. And so then I can label them as either part of, again, a specific track. And this has been applied to Proto-DUNE with success. So in summary, the CNN-based regression event energy has shown better performance than the traditional method for both new ECC and new mu-CC events. We also have great performance with CNN-based event classification with greater than 90% selection efficiency at maximum for both new ECC and new mu-CC in both the FHC and RHC samples. GNNs and sparse CNNs have also shown a lot of promise and continue to be worked on. And lastly, these improvements compared to the traditional estimators will give us improved measurements of the oscillation parameters and also will help us get the most out of our data. Thank you everyone for listening.
Okay, thank you very much for the talk. Is there any question? Okay, no, I don't see any question. So finally, we arrived at the end of the session. So thank you to all the speakers. I see in the chat there is a question about the poster session. So maybe is there one of the organizers present who knows about the poster session? Okay, I'm not sure. I think the poster session will be in a different room. So as far as I know, there is a dedicated poster session, but I think this information should be on the Indico site.
Yeah, I can confirm. The poster session is in another Zoom room, and the link is at in the timetable or the links to all sessions in Indigo program. So you can connect from there.
Okay, thank you for this information. And so I think we close this parallel session here. Thank you.